No? Can we turn it on? Okay. Welcome. My name is Gordon Wettstein, and it's our pleasure to be here today. And we'd like to help you understand how to build your own head-mounted display. So this is a course targeted for people who just want to understand what's going on inside head-mounted displays and in virtual reality displays. Also for people who may think about teaching virtual reality at your institution. We've been teaching this course over the whole semester for 2 years now, and Robert, Nitish, Hayato are my TAs. So they're going to be showing you demos and talking about certain parts of the course. And then also, if you want to build your own head-mounted display or do something experimental, we've seen a lot of cool demos at eTech this year. If you haven't had a chance to go there yet, definitely check it out. A lot of the components we're using, like the displays, lenses, the IMUs, and so on, are also being used for a lot of these experimental setups. So if you're interested in tinkering around with any of these components, we've been putting together this course for the last 2.5 years or so, and have been iterating around it, and we'd be also very happy to get feedback from you on how to improve it after. So feel free to come up to the podium or send us an email on what you think could be done to make this better. So let me start with a really boring definition of what virtual reality is that I just pulled from the internet. And in that definition, it says that virtual reality is the computer-generated simulation of a three-dimensional image or environment that can be interacted with a seemingly real or physical way by a person using special electronic equipment. So the focus of this course is really on that special electronic equipment and the algorithms driving it. So we're not going to be talking about content creation or Unity or game development or things like this. We really want to look at the technology here. And this is really dry kind of a description of virtual reality. For most of you who think about VR, we think about something like this, right? It's really an experience, a multimodal experience that includes visual cues, auditory cues, haptic cues, interaction. You're doing something really exciting. And in case you haven't had a chance to see too much VR demos yet, I mean, there's the whole VR village in the experiences hall here at SIGGRAPH. This is the best place for you to experience a lot of really cool things in this space. VR is interesting for many different things. We usually think about gaming and entertainment as one of the applications, but there are many other applications beyond that, including simulation and training, visualization, of course, entertainment. But even if you think about minimally invasive robotic surgery, like the Da Vinci robotic surgery system on the lower right there, that's already in use and being used for hundreds of surgeries every day across the country. So in that case, the surgeon actually remotely operates the robotic arms that are actually performing the surgery, and he looks into the box, which is basically a virtual reality system with a live streaming feed from the endoscopes. So VR is applicable and important for many, many applications, including also architectural walkthroughs or remote operation of vehicles. Just a couple of days ago when I got to the hotel here, I was actually watching the drone racing world championships on television. I didn't know that existed, but these guys are flying their drones with head-mounted displays. So, that's an exciting application too. Personally, I'm very excited about education and just communication in general, all the usual things that people talk about. But I think in summary, VR is a new medium, and we should think about it as such. We don't really know exactly how to create all the different possible experiences with that, but it offers a new platform, and that's what makes it so exciting from content creation side, from the technology side, and so on. So we shouldn't think about it as a bigger television or a bigger gaming platform. It's really something new, and over the next few years, we want to learn how to use it, how to create content for it. So it has the potential to create, I would say, unprecedented experiences that we don't really know yet, and that's going to continue, hopefully, for the next while. So I like this drawing from Alice in Wonderland, for example. I mean, VR has the potential to really drive you down that rabbit hole and, experience things that you couldn't experience with any other medium today. We're engineers, so for us it's particularly exciting to see that the National Academy of Engineering in the US declared enhancing virtual reality as one of the 14 grand challenges of the 21st century. So in this case, it's really all about the tech. And the tech doesn't just include the display, of course, but a lot of different aspects. So for me, what's exciting from the engineering side on VR and AR, of course, too, is that there's such a diversity of different things. My colleagues at Stanford work on, VLSI. They think about chip design, about architecture to drive this at low power, low latency in a wireless setting. I love human perception, displays, but also cameras and sensors to do scene understanding, hand tracking, gesture tracking, positional tracking of the device. We want to think about how to create content, for example, cinematic content. How do we capture a VR movie, right? We've seen a lot of different cameras emerging over the last few years, and Robert's going to tell us more about that, but also how to share these experiences and doing all of that in a wearable form factor. So this is a grand challenge on the engineering side as well as on the content creation side. And the goal of this course is to take first steps in understanding the basic components of these displays. Right now, most AR/VR displays are pretty big and not really in a form factor that we'd like to see them. Like eventually, we'd like to see something like this being an AR display, but we're not quite there yet. But one thing that we've learned in Silicon Valley is that in a matter of years or maybe a few decades, we can go from a computing system that fills an entire room to something that sits in your pocket. So if you think about the processing power of your cell phone today, it's about 1,000 times more powerful than the computer that was on the Apollo mission that propelled man to the moon. And that's only been a few decades ago. So we can only envision what AR/VR systems or wearable computing systems in general will look like in the next little while. And you can think about this as a natural progression from desktops to laptops to mobile phones to wearable things. But in fact, VR/AR has been there in some form or another for a long time already. So everybody who talks about the history of VR will probably tell you a slightly different history. So here's my take on this. We're going to start in the early 1800s, in Victorian times, when people would gather to watch stereoscopic photographs on the stereoscopes. So the Library of Congress in the US actually has a large collection of stereoscopic photographs from the American Civil War. That was a little bit later than this, but there's a lot of content out there for stereoscopes, and it's a nice gimmick. We've seen a big step forward in the late 1960s with people like Ivan Sutherland working on electronic head-mounted displays. And that was also kind of the birth of computer graphics, because with these types of displays also came the need for using algorithms to synthesize an image that you can put on the display that would try to mimic the real world. First consumer products already came out in the 90s. Nintendo had the Virtual Boy out there. How many of you have tried the Virtual Boy? Oh, quite a few. Okay. It's exciting. It had most of the basic components, but it wasn't quite there yet. It actually sold more than 700,000 units, so it's quite a lot. But I think the computer graphics wasn't quite there yet, the chips. So now over the last 5 years, we've seen an explosion in VR displays with consumer products being pretty much everywhere. And what we think about in an academic context is first how do we teach our students how to use this technology and how to build it, but also how to build the next generation of this technology. Okay, so looking back at the stereoscopes, the fundamental principle of operation is very simple. You just have two different images that are being presented to each of the eyes, and that's a stereoscopic 3D effects. Today's head-mounted display generation operates in a very similar fashion. We have two lenses and two images, one for each eye. Now, of course, we have dynamic displays, we have inertial sensing, we have shared experiences, we have a lot more processing power from the GPUs, so we can generate different experiences, but the fundamental principle of operation has not changed all that dramatically. Taking a closer look at Ivan Sutherland's Sword of Damocles here, that was the first optical see-through augmented reality display. He had beam splitters, so you can see the real world through it. There are 1-inch CRT monitors on the side that present a stereoscopic stimulus. There was already head tracking using mechanical and ultrasonic tracking. There was, model generation. I mean, he was just rendering a wire cubed, but I mean, that was revolutionary at the time because the graphics didn't exist, basically. But he later invented also the sketchpad and a lot of really interesting ways of how to interact with this content, because at the end of the day, we can build the display, but what are we going to use it for? We want to use it for generating experiences, so the human-computer interaction side is extremely important here. So this is the Nintendo Virtual Boy, and there's a screenshot from one of the games, Red Alert. That's one that I played a few times. As you can see, it's just line graphics. So it's very, very primitive. There's no occlusions. It is stereoscopic, but the experience is quite limited. So you can try it yourself. They sell them on eBay still. If you're interested, it costs about $100, $150 or so. It's interesting. So now where have we gotten from the stereoscopes to today's generation VR displays? Well, as I said, they became electronic or digital in the 60s. People like the folks from VPL Research in the 80s have added a lot of the interaction side and haptic feedback and other ways of interacting with the content. But it's only been in the last 15 years or so that the cell phone industry has made tremendous progress in building low-cost, high-resolution displays that are suitable for creating a VR experience, and also low latency, low power, low cost inertial measurement units that can be used for orientation tracking. And that's absolutely critical. So if we look at a teardown of a Oculus DK2, for example, I mean, you can look at the components, and they're not even trying to hide that there's a cell phone screen in there, right? So arguably, the cell phone industry has really been enabling this trend, this recent revolution of VR. Of course, there's a lot of custom electronics, but mostly these are IMUs on there and other tricks to do positional tracking. We have a lot of injection molded plastic, a couple of lenses, and we'll go through these components in more detail throughout the course and really understand what's inside. So everybody who sits in this course should be able to walk outside after and be able to just implement all the graphics, all the inertial sensor fusion with their own head-mounted display at the end. And the course notes will all be up online, so if you actually sit down and program it, you can always use these as a reference. So I think the DK2 was great for many reasons, but one of them was the field of view. Creating such a large field of view is just something that creates a completely different experience for the user. It creates this telepresence, the sense of being somewhere else. And you know, the optical design of current generation head-mounted displays is still very simple. It's actually called the simple magnifier VR display, and you can find these from most companies now. Sony ships it with the PlayStation. We have the Oculus Rift, HTC Vive, but there are a ton of different clones. But the principle of operation is the same for all of these. Two lenses in front of a microdisplay. If we think about AR displays, and we're not going to talk about AR displays much in this course, I just want to highlight the difference on how it's different. In an AR display, you want to see the real world, ideally optically unobstructed. So I want to see all of you just like I am now, and then I want to digitally superimpose virtual content on top of that. And the design that Google Glass, for example, used is very simple. We have an LED that acts as a backlight. We have a liquid crystal on silicon, spatial light modulator there. You can think about this as a reflective LCD. And then we have a little curved combiner on the right that projects the image and magnifies it into the eye of the observer. And the observer looks through a beam splitter so that they can see the real world and the digital world both at the same time. So this principle of operation has also been around for a few years now. It's usually known as Pepper's Ghost, being used in theater and other types of on-stage experiences where you'd have a large beam splitter on top of the stage, so you can see the actor, and the audience doesn't see what's going on under the stage, but there's the ghost or a person dressed up as a ghost under the stage being lit up. They reflect, the image reflects directly to the audience, and the audience will see the ghost as if it's appearing on the stage, and then you can, you know, do crazy tricks like that. I think the frontier of engineering AR displays right now is in the space of waveguides. So to get to the form factor, like a pair of glasses that's comfortable and small, we need to create a thin waveguide with a small projector that emits an image into the waveguide on the one side, and then the eye picks it up on the other side. And ideally, we want to be able to correct the prescription of the user. We want to be able to have it light, low power, and very thin. So waveguides are a great topic for research right now, a lot of interest in that space, and we're not going to talk about it more in this course. We're going to focus on the simple magnifier design because that's something that every student can implement also in the course. So here's just a slide on the instructors for today's course. My name is Gordon Wettstein. I'm an assistant professor of electrical engineering at Stanford and also affiliated with the CS department there. Robert, Nitish, and Hayato are research assistants in my group, and they're also the TAs for the course on VR that we've been teaching for the last 2 years. So they've probably answered 1 million Piazza posts by students, and they can answer all your questions that you may have. We'll stick around after the course as well. So if you have questions come up, everything we show you is going to be open source. Most of the stuff is already online. And yeah, we'd be happy to share anything that we're showing you today. So we've worked on a lot of different projects in related spaces. I've been working on displays actually for the last 10 years maybe, and you may have seen layered 3D tensor displays and a lot of these layered light field displays that we've been publishing in the technical paper part of SIGGRAPH over the last maybe 10 years or so. Over the last few years, I've become very interested in head-mounted displays or wearable electronics in general. And with my students, we've been publishing a number of papers on varifocal displays, light field displays, monovision displays. And if you're interested in these more advanced technologies, I recommend taking a look at the technical paper session or at our other papers that we're presenting. We're not going to talk so much about these advanced technologies. This is really an introductory course for people who start out with zero or very little knowledge in this space. So for example, this morning there was a big session, Time to Focus. It was a technical paper session with a couple of different papers on how to drive accommodation or generate focus cues in near displays. Some of you may have seen this. If you're interested in these advanced topics, take a look at these papers. The session is already over. Tomorrow is another session in the afternoon. That's a talk session, so this is not a technical paper, but talk. And Nitish is going to be talking about optimizing virtual reality, using gaze contingent focus for all users of all different ages, how to do prescription correction and make this technology really accessible. So that's going to be tomorrow afternoon. And there are some other relevant papers in that session as well. Coming back to this course, again, as I said, we've been teaching this for 2 years at Stanford. Here's a photograph of one of our labs. It's a hands-on class. We have 2 lectures per week and a lab. This is one of the labs, and everybody basically builds the head-mounted display throughout the semester. So it's really a lab-based class with the theory and hands-on assignments, because I believe that virtual reality is really something you need to sit down and experience, and that's also the experience we wanted to create with this course. So think about it as one big project for a whole semester, and every week we teach a little chunk of that, starting with the computer graphics pipeline and so on, basically the same approach that we're taking now in this course. And then the students have an assignment and a lab at the end of the week, which is implementing that assignment. Next week, they're going to implement the next part. And at the end, they have the whole head-mounted display ready. So the learning goals for this class are, we want to teach students and you the fundamental concepts of VR technology and also computer graphics. And again, it's an introductory level course, so hopefully we don't, we're not too repetitive, but we want to make sure we don't lose anybody. The prerequisites, if you actually want to implement this, is that you need strong programming skills, I would say. So we don't teach that in the class so much. And you also have to have basic knowledge of linear algebra. So just to give you a sense of how many students there in this class, it's about 80, and we have undergrads and graduate students. And in teams of 2, they get a hardware kit that we'll show you in a second, and that's what they're going to be using for the class. All the material for the slides we're showing you today, all the software, all the hardware are available on our course website. You can see that right here. We're constantly in the progress of revising the assignments and other things, but you can use that as a guideline if you are interested in teaching this course too. So here's an overview of what we're going to be doing today. I already gave you an introduction overview. I'm going to show you a little bit of the hardware and software right now. Then Robert's going to talk about the graphics pipeline for a little while. So if you know everything about the graphics pipeline already, that's where all good things start in computer graphics. At the end, you'll have a teapot on your screen just to prepare you. So that's going to be interesting, but also very introductory. But we'll also talk about stereo rendering, how to set up OpenGL for stereo rendering, and lens distortion for OpenGL using shaders. So there's a lot of VR-specific graphics in there as well. I'll be talking about inertial measurement units, orientation tracking, and positional tracking, and the experimental hardware that we're using in the class that's actually low cost to implement all of this. Then Nitish is going to be talking about spatial sound, and Robert's going to be talking about cinematic VR and how to build, a VR camera if you want to at home as well. And then at the end, we'll have time for Q&A, and we'll be hanging out, showing more demos. Hayato is actually going to show demos throughout the whole course. So at the end of each section, he's going to show a live demo of, what you can implement and what the students also do. All right, so let's talk a little bit about the hardware and the software that we're using for this class. Basically, every student gets a VR kit. We have the detailed list in the following and also on the website. So if you want to reproduce this, you can just go on the website and order all these parts. We have a head-mounted display housing and lenses. We have a small LCD that is pretty high resolution, has an HDMI driver board, so you can just hook it up as an external monitor to any computer. We built a shield, the Arduino, which is what we call it, for the Arduino. So with this shield, you can plug in an IMU for orientation tracking, and you can also do positional tracking. And we'll show you how that works. We use it as an external monitor for any kind of a laptop or desktop. And a lot of the students actually work with these flex sensors or vibration motors for their projects to build input devices like a data glove or haptic feedback. So these are very easy to use together with the Arduino. So the head-mounted display housing is a ViewMaster VR starter kit, or the Deluxe VR viewer from ViewMaster. This is the same as the old VR viewer. It's made for a cell phone, but it's actually very robust, and we can use our LCDs and just put them right inside. We drilled a hole on the side so we can route the cables into it, and they're pretty inexpensive. We got them last year for $15 from Walmart.com. The deluxe version is a little bit better, and that's now about $23, but the prices are going down, so we can actually afford to buy like 40 of these for the class to give out for the students. They implement the Google Cardboard 1.0 or 2.0 standard, depending on which one you get, and they're quite good. The LCDs we're working with are from Top Zone. That's a Chinese company in Shenzhen. We found them somewhere in Alibaba, and everybody who's been contacted them has been able to order these kits. So the LCDs come either in 1080p, so that's 1920 by 1080 resolution for $90, or in the 2K version for $100. And that already includes the HDMI driver board. So without the driver board, it's very difficult to drive them. With the driver board, you just plug in an HDMI cable and it runs. Okay? If you get the driver board, don't get the audio jack. The driver board has an optional audio jack that is mechanically very awkward and makes it difficult to fit into the housing, so we usually get them without. So they're a little bit flimsy, right? It's just an LCD panel that you'll find in your cell phone already. It's basically the same thing as in my old Nexus phone. But the ribbon cable is a little bit flimsy. That's why we use the housings that are reasonably robust and shield them. And we broke only very few in the course, so it's almost safe to give them out to students. Ideally, you want to use something like an OLED, but we haven't really found low-cost OLEDs at that size that we can use for the course. If you go to eTech, a lot of the displays that you see there are actually driven by exactly this display too. So I recommend it because it's easy to work with and reasonably low cost. We've actually done a lot of modifications to this too. One of my TAs built a custom PCB that we can use to intercept the signal between the driver board and the LCD, so we can strobe the backlight. Remember that LCD switches at about 60 hertz, but the LED backlight can actually strobe at much higher rates. So if you want to play around with persistence or other options, you can actually do that with the PCB, and we'd be happy to share the design files for all of this too. The other important component that we're using is the Arduino. And the Arduino is really just a little plug-in, a hardware plug-in for the Arduino. It's all open source. We use it for orientation and position tracking and to interface with other I/O devices, like the vibration motors, flex sensors, or other things. It's custom designed for our course by Keenan Molnar. The design files are all on the website already. If you want to reproduce it, modify it, go ahead and do it. It's already online. It uses a Teensy 3.2 microcontroller, so it's a little bit more powerful than the regular Arduino Unos because it runs at 48 megahertz, but it's only about $20, right? So it's actually very reasonable. The IMU we're using is an InventSense 9250 that has 9 degrees of freedom, has a 3 accelerometer, 3-axis gyro, 3-axis magnetometer. You can read it all out with the Arduino and do any processing on the Arduino. We just basically stick it right on the shield, and that costs about $6 if you buy it on eBay. We also have these photodiodes on the side, and we use these for positional tracking, as I'll show you later, and these are less than $1. The same photodiodes that are being used for the HTC Vive Lighthouse tracking system. And we basically reverse engineered that and hacked it. It's not quite as good, but it's good enough for a course and for hobby projects. So again, the Teensy, the Arduino, you can just program it through your Arduino code base, the IDE. We have the IMU on here. We have a couple of pins that we can use for changing hardware setups. The photodiodes that include the digitization and amplification of the signal are here. Everything's online. If you want to reproduce this board, you can do that right now. We have the exact locations of the photodiodes here that you'll need for the tracking later. The photodiodes are connected to interrupt pins on the Arduino, so we can detect rising and falling edges just to do the time stamping. If you have no idea what I'm talking about, let's wait for a later part of the course. The IMU is just connected to the Arduino via I2C. That's the most common protocol for communication on the Arduino, and is already connected for you, so you can use any wire library or I2C library to program this. The GPIO pins basically break out other pins that are not accessible on the Arduino anymore, and you can use that to hook up flex sensors, vibration motors, other GPIO things. So here's just a photo of one of the many projects that the students in the class built, which is basically a data glove that you can track the flexing of your fingers, and you can feedback, tactile feedback using the same thing. So now Hayato is just going to show you a quick demo of the full setup, and maybe you can hold up the head-mounted display first, and then we'll walk through the individual parts later on. So we should switch the monitor here. Maybe I can show you the headset. So here's the ViewMaster with the display inside. We have the vArduino. It's just glued basically to the front with double-sided tape. We use it for orientation tracking, positional tracking. We'll go through the individual parts, and you can come up to the podium after the session if you just want to try it out yourself.
Okay, so this is the scene that you are going to render after this course. You are going to use the orientation you estimate on Teensy and stream the data into your computer by using a WebSocket and render the scene with WebGL on your browser. As we are going to explain in the following session, students are going to make small building blocks for this rendering to understand the technology behind the head-mount display. And as Gordon has already explained, we decided to use JavaScript, WebGL, and also Arduino Teensy as a development platform. By doing so, the development became much more easier than using OpenGL and C++, and we can allow you to use your laptop very easily without almost any preparation, because I assume you have a browser and also your favorite editor on your laptop. And also, we decided to use a library called 3JS to hide all of the cumbersome low-level WebGL API calls. By doing so, the whole code base became much more accessible to students who are not very strong about programming. If you know about 3JS, 3JS is known to be a really good library to render a scene without almost using a math. But we have exposed almost all of the mathematical operations that is required for rendering to let you implement it by yourself.
Do you want to turn on the lens distortion?
Yeah. Yeah, so we are going to provide some physical parameter of the head-mount display, so you can use lens and distortion shader as well, that you are going to learn in the following session.
Okay. Cool. Thank you, Hayato. So everything Hayato showed you, at least the rendering part and the lens distortion, I'll be covering now. Then Gordon will talk about things involving the IMU. So I will be talking about the graphics pipeline, specifically the rendering part, stereo rendering, and lens distortion. So before we can get to something like this that you'd like to see on a VR display, let's start with something a little bit more simple, something like this. So what do you guys think is happening in this image? Finding pose? A reclining pose. Yes, that is happening. But the part I'm interested in is specifically the grid pattern this artist is looking through, this mesh, and him essentially drawing whatever he sees through this grid pattern onto this parchment paper that is also essentially a grid line, right? So this is the essence of computer graphics, which is projecting a 3D environment, this woman, for example, onto a 2D piece of paper. So we're going to start off with the graphics rendering pipeline in this talk, like I showed. We'll talk about coordinate space transformation, some shaders. Then we'll talk about stereo rendering, specifically how to operate the view matrix and the projection matrix to get the stereo rendering to be perceptually correct. And then we'll talk about lens distortion, how to do that in the fragment and vertex shaders. So as Hayato mentioned, we're using WebGL for this as a framework for this course. And the reason we use it is essentially can be implemented on all browsers. The one shown here, it can be implemented on tablets, on smartwatches, on smartphones, and those of you that watch Silicon Valley now on smart fridges. So, you know, we wouldn't want to strap a fridge to our head, but the point is that these are pretty ubiquitous and we can put it on any platform we want. So it's easy to develop on a computer and then throw onto a phone afterwards. And also it doesn't require us to have compiled code that we have to worry about, you know, supporting various types of hardware for the different computers that students have in our classes. Also, as Hayato mentioned, we use the 3JS framework, the library, to operate on a higher level so we don't have to mess around with very low-level WebGL code. But we expose the important mathematical constructs for students to understand the underlying principles. So computer graphics, at the most basic level, it consists of converting a 3D scene to a 2D image. What do we need for this? We need some 3D geometry, some transformations, some lighting, and material properties and textures. Now, to represent an object surface as a set of primitives, we have a couple of primitives to choose from. We have points, lines, triangles, and quadrilaterals. And the process of combining those primitives and creating a mesh from that is called tessellation. So once we have some 3D model, as described as a set of primitives composed of 3D vertices, what do? Well, how do we get that image onto a screen? We go through the graphics pipeline, which first consists of a series of stages. First, vertex processing, where we transform individual vertices and their corresponding attributes. Then the rasterization process, where we convert each primitive into a set of fragments, followed by a fragment processor, which can operate on individual fragments. And then finally merging all of this together into something that we can display on the screen. And each of these stages I'll talk about very briefly now, but they all hold their special parts in the VR pipeline. So the coordinate system that we're going to be dealing with is the right-handed coordinate system, and there are a couple of stages in this pipeline. There's the object coordinate, which defines the space in which each individual 3D model is defined in. Then the world coordinates, where we can place different objects or different models relative to one another in this world space. Then the viewing coordinates, where we then rotate all of these objects in this world space around a camera that we want to show, that we want to have a certain viewpoint of this world space. And then we project that using a projection matrix transformation into a clip or normalized device coordinates. And finally, we can put that onto the window, onto the screen. So starting with the vertex transforms, this can be broken down into these coordinate transformations that I was just talking about, starting with the model transform, where we arrange objects in the world, individual objects. Then we have the view transform, where we position and orient the camera so we can get the correct viewport that we want of the scene, followed by the projection transform, where we essentially select the camera lens that we want to imitate when looking into this scene. We can adjust the focal length and the zoom of the camera and set the camera's field of view. Once we have this projection transform, we can finally print whatever this camera captures of this 3D scene and display that on the screen. So starting with the model transform, like I said, we want to transform each vertex of the model to some world coordinate space, essentially orient different objects that we have defined relative to one another in this world space. So we can do this with a series of homogeneous transformations. So we have translation, rotation, and scale to play with. I'm not going to go into detail about any of these. This is just very basic computer graphics. But we have all the matrices defined here and also their inverses. So we can essentially create any combination of these operations by just multiplying these matrices or multiplying one of the vertices of initial model by a series of operations or that I just described here. And you can perform the inverse of this by multiplying the vertex by the inverse of each of these matrices in the reverse order. It's important to note that the rotations and translations are not commutative in general. So you have to be sure to perform in the correct order, or else you're going to start getting kind of wanky data. So let's move on to the view transform then. So this one's going to be very important, specifically for setting up stereo rendering. So far we've discussed model transform, which goes from object space to setting up some scene, specifically your world space. The view transform is a simple 4x4 matrix transform that is sufficient to go from the world space to camera or view space. And this essentially defines a camera in your world space and defines its orientation. So what this allows us to do is essentially it rotates everything in the world around this camera, and after we perform this transform, we look down the negative z-axis that I'll show you later. So an abstraction to this that we use and is commonly used is defining these three vectors to define the position and orientation of a camera. And the eye position is considered the center of the camera. The reference position, or the center vector here, defines the point to which we want the camera to look towards. So essentially the camera looks along the vector defined by the difference of the center and the eye vectors here. And the up vector defines the up vector of the camera. Using these three vectors, we can define three bases via some cross products that allow us to create the rotation matrix that the view transform is composed of, as well as the translation matrix. So a view transform is essentially just a simple translation and rotation, and that's essentially the underlying principle here. So we can define this view transform as just the multiplication of these two matrices. And then we're going to modify this a little bit when we get to the stereo rendering, and I'll show you how. So you can combine these into one matrix effectively. So where are we now? So we're now in camera space. So when we take a vertex, multiply by the model matrix, and then multiply by the view matrix, we can combine these two matrices into a model view matrix that defines the conversion of a vertex in model space directly into camera space. And this view transform, as I was mentioning earlier, is just defining your camera somewhere in world space and then rotating everything around the camera using this view transform. Because this transform is applied to every single vertex that you have defined in your scene. So the projection transform, which is the next one, is similar to choosing the lens and the sensor of the camera that you're trying to mimic here. And specifically, you can specify the field of view and the aspect ratio. So in the simplest form, you can create a symmetric perspective projection where the field of view along the horizontal and vertical directions can be different, but it's symmetric around the center of projection. And you can define it using this matrix here. I'm not expecting anyone to remember this, but this is one way of defining a projection matrix. And of course, there's actually going to be a little bit of math in these slides. So all of these are going to be posted online, or actually they are already posted on our course site, EE267 at Stanford. So if you want to come back and look and find any of these equations, just head over there and you'll find everything that you need to find. The more general version of this is the asymmetric perspective projection, where we define it as the intersection of some frustum with a near clipping plane or a near a rectangle at the center of our projection, and we define it as this matrix here. And the four important parameters are the left, right, bottom, and top corners of the intersection of that frustum with this near clipping plane. And we're going to be using this actually pretty heavily when we implement the stereo rendering in a couple of minutes. So the model view, okay, so where are we now? So we have the model matrix defined, we have the view matrix defined, we have the projection matrix defined. If we multiply all of this by each of the vertices that we have defined and placed in the scene, we get a vertex in clip space. And clip space is just a normalized volume, a normalized space where all the dimensions are between -1 and 1. And to go from clip space, we go to normalized device coordinates by finally performing the perspective division by dividing each of the coordinates x, y, and z by the last one, and this effectively creates the perspective divide that gives us this sensation of depth. Or perspective, rather, that the initial artist at the beginning of this section was trying to convey. And then we can convert this to the viewport with the viewport transform also in matrix form that I'm going to omit for now. But this essentially creates the mapping that we end up picking onto the pixel, end up projecting the information onto your window, which ends up mapping to the pixels on your display. So we're done with the coordinate space transforms. We'll come back to the view and projection matrices in a little bit. But for shaders, we should talk about shaders, which we'll need for the lens distortion section. So shading, you can see here in the graphics pipeline, we have two parts that are programmable, the Vertex processor and the fragment processor, and each of these are able to operate on individual vertices and fragments individually and in parallel. They're small programs that execute on the GPU and can operate on vertices or fragments. The Vertex shader we use to perform all these transforms that I was just talking about, as well as per vertex lighting, and can also implement lens distortion that we'll need. And the fragment shader can essentially assign the final color to the fragment. It can also perform lighting and lens distortion, as we see here. So the Vertex shader takes in some vertex positions and their corresponding attributes, takes in the model view matrix, projection matrix, and normal matrices, and is able to output, does some operations. It can be whatever we want. It's programmable, so we can define whatever happens in this shader. And in the end, it will output a transformed vertex position in clip coordinates, as well as the corresponding attributes. The fragment shader, on the other hand, is going to take the output of the rasterizer, which is essentially an interpolated version of, it's taking a bunch of fragments that are interpolated information from the vertices, can do some operations, and finally output some fragment color and depth that are necessary to merge the output and to choose which fragments end up being displayed on the screen itself. So essentially the closer fragments will end up being displayed, and the ones that include objects in the back or fragments behind it, the ones behind the front fragments will get removed and won't be displayed to the screen. So why do we need shaders? They're massively parallel, and this is great for GPUs, which take advantage of this type of operation. Vertex shaders operate independently on each vertex, and fragment shaders operate independently on each fragment. So it allows us to do, as I mentioned, in the Vertex shader, we can do vertex transforms, and we can also do lighting and shading calculations, such as Gros shading or Phong shading. These are very simple, and we teach this in the class. We're not going to go over this now. But for just kind of getting people that maybe not have taken computer graphics initially, these are good things to start the class with. And we can also do more complicated things like rendering motion blur, rendering depth of field, some physical simulations. We have the users actually, the students in the class implement depth of field rendering and foveated rendering that will also omit for the purpose of this particular course, because we're only limited to 3 hours. But we have the students implement each of these operations in the class. So for the shading languages that we have at our disposal, we have CG, introduced by NVIDIA, that is deprecated for now. GLSL, which is the shading language for OpenGL, and WebGL, which is the one that we end up using. And there's HLSL, which is the corresponding one for Direct 3D. So like I said, we use the GLSL programming, or the shading language, which is just a high-level programming language for shaders. It allows us to avoid a lot of the nitty-gritty stuff that goes under the hood. Its syntax is similar to C, and usually very short programs that we just implement on the GPU itself. And there's a bunch of tutorials on this stuff. I'm not going to go super detailed into the shaders, but you can find those references online. So there are many versions of GLSL. The one that we end up using, we're forced into because 3 doesn't support WebGL 2.0 yet. So we are stuck with using WebGL 1.0, which is based on OpenGL ES 2.0, which forces us to use GLSL version 1.1. There's a lot of different versions of GLSL out there, so if you're online and looking for some function that you want to use, make sure to check which JLSL version is supported in. It may not be supported for JLSL 1.1. I've come across this problem multiple times, and the errors that the WebGL compiler spits out aren't very pleasant to debug and figure out. Okay, so that essentially covers the overview of the graphics pipeline. So now we can get to actual VR stuff. That was just a basic introduction that I needed to do to kind of get through the rest of this section and also some of the other sections of the course. So stereo rendering. Before we get there, let's talk about depth perception. So here's an image, and we can clearly understand that there's relative, well, we can understand the scene pretty well, right? We know that things further away in the back are, well, we can tell depth and through relative occlusions. We can figure out kind of a pretty good scene understanding. So we have many monocular cues and binocular cues to choose from, but not all of them are supported when we just look at this image on a screen right now, right? So we have things like relative object size to use, perspective, absolute size, occlusions to have an understanding of the scene that's going on here. So, but if you notice, everything that we've supported doesn't include any of the binocular cues, which is what we use in the real world to get a really good understanding of depth. If we were to only rely on monocular cues, catching, balls that are thrown at us or avoiding a tree when we're skiing become a lot more difficult. We actually rely on having two eyes to be able to do all of these things. So let's talk about some of these additional really important depth cues that we end up using on a day-to-day basis that we don't even realize, but ones that we have to support to make VR really convincing and really, really immersive. So we're getting to the point where things get a little bit more interesting. So our depth perception, some of the depth cues I'll be talking about now start off with binocular disparity, which is the relative shift between the images that we perceive. And binocular disparity drives something that is called convergence, which is the relative rotation of our eyeballs. So if I look at something that's very close to me, my eyes rotate inwards, but as I look somewhere further away, my eyes rotate outwards. So this is convergence. We also have a very strong depth cue in motion parallax, which we can essentially see day to day. If I just shift around on my feet and kind of move my head around, I can see certain objects starting to occlude other objects that might not have been before. Motion parallax is a very important depth cue. And finally, we have accommodation and its corresponding retinal blur. And this refers to kind of the focus of our eye. So if I look again at my finger that's very close, everyone behind me or everything behind me is blurred out very significantly and vice versa. So all of these cues are very important for our perception of depth. So let's see kind of where are we in the VR game, what can we support right now. So current generation VR displays or stereoscopic displays can support these first two. Actually, you wouldn't really be called a VR display if you couldn't support these first two in binocular disparity and convergence. And this is just displaying the correct stereoscopic stimuli on the displays that I'll actually show you how to do in the following section. And also, any current VR display that supports motion tracking or positional tracking can also support motion parallax. So the HTC Vive and the Oculus Rift both have positional trackers and can support movement and can support updating the rendering to create this motion parallax effect. And this adds this additional kind of depth cue that suddenly makes these devices much more immersive. Devices like the Samsung Gear VR or the Google Cardboard don't have positional tracking, they only support orientation, and we then don't have this motion parallax cue. So if you're wondering why you kind of feel more immersed in some of those devices that have positional tracking, this is the reason. Then we have, in the near term this is still an active area of research, we have light field displays, which can now support accommodation and retinal blur cues. There are many other displays, actually this very active area of research as to how to support these cues. It's not as simple as it might seem. There's a whole session in the morning talking about how to drive focus and accommodation to different planes. So we have light field displays to look forward to in the near term, hopefully. Also this morning, even longer term displays are holographic displays that can actually recreate the wavefront entering our eye to match exactly what we perceive in the real world. So this is initially maybe thought as a kind of a long-term goal, but maybe we're closer than we initially thought, as shown by Angel Maimone in the session this morning in Time to Focus. So let's look at how important these different depth cues are for us at different levels of depth. So if we look in the bottom left corner here, we can see that convergence and accommodation, they're very important for things that are quite close to us. Accommodation specifically is very important as a very important depth cue for anything essentially within arm's reach. So the reason everyone is trying to support accommodation in these newer generation VR displays is as we start developing haptics and devices where we start using our hands in these VR displays very naturally, we're going to inherently want to support accommodation for things that we're going to be picking up that are going to be very close to us. Then we also have motion parallax, we can see above, that is quite important for longer depths. We have stereopsis, which is also quite important for longer depths. And as we get very far away, then relative size and occlusions they're very important throughout the entire range. So let's talk about stereopsis a little bit more in the stereo rendering part of this talk. So stereoscopic displays, as Gordon mentioned earlier, have been around for a long time. Back in the 19th century, actually. So the idea of a stereoscopic display is that we present a slightly different image of the same scene to each eye. As you can see here, these two images look very similar, but as it's flipped between them, it's actually pretty obvious that they're slightly different. So if we were to put on that, old school Viewmaster essentially and look at this Abraham Lincoln, he'd have this kind of three-dimensional structure to him. We would think that he's kind of popping out of the screen. So we are able to generate these stereoscopic images, and but before we can do that, we have to learn about parallax. And parallax is this relative distance of a 3D point projected onto two stereo images. So if you have a projection plane placed somewhere in space, then what we have is if we have a point behind this projection plane, it's going to pass through two different points on this projection plane, right? And this is going to create positive parallax. If the 3D point is placed at the distance of the projection plane, both is going to appear in the same position on both eyes, and this is going to be the zero parallax case, and the negative parallax would be if the point is in front of this projection screen. So generating this parallax effect or generating these stereo images, there's kind of a right way and a wrong way to do it. And let's see how that works. So our visual system only uses vertical parallax. That's actually very disorienting when you start seeing vertical parallax. So we're very sensitive as humans to any vertical parallax that we see, and actually it becomes very uncomfortable if we start seeing images with any vertical parallax whatsoever. So there's two typical ways of capturing these stereo images. One that essentially tows in two cameras. So instead of having them completely be parallel to one another and pointing out into the scene, it tows them in slightly, as we can see on the left here. And what you can see now is that its projection planes, they aren't in a single plane. And what that results in is that if you look at the left sides of these projections, they don't appear at the same depth, and this results in having slightly different magnifications of the objects that are projected onto them. So what ends up happening is you have actually, because of the different magnifications, you start generating vertical parallax at these extents of the images. Close to the center, you would still see roughly the correct parallax information that you'd expect, but along the edges of these projection planes, you start seeing artifacts. The right way to do this would be to have just place two cameras and offset them horizontally, and then generate this with render this out with an asymmetric viewing frustum that I'll describe in a little bit. So this is an example of parallax done correctly. If you had anaglyph glasses, you would see that this would be popping out at you. Actually, in this lecture in our class, we distribute anaglyph glasses to everyone, and then they just end up looking at these anaglyph images the entire time. Actually, this has been kind of well known again, I guess, since the 19th century, and people have figured out how to do parallax correctly even back then. This is not a good way of doing vertical parallax. If you can see again on the edges of this image, you can start seeing the rope that these birds are sitting on, the electrical wire. There starts being some vertical parallax, and this, if you were to view with your anaglyph glasses, would be very uncomfortable to fuse. Or actually, you just probably wouldn't be able to at all, because this is quite a lot of vertical parallax. So now that we've talked about parallax and some basic the idea of stereopsis, let's talk about stereo rendering specifically for head-mounted displays. Now, all current generation VR head-mounted displays just act as simple magnifiers, meaning that it essentially consists of, as Gordon showed earlier, just a microdisplay placed behind some static optic. And what this does is essentially it magnifies this microdisplay and projects it outwards and fixes it at some distance. And now the distance to this, what we call a virtual image, is defined by certain parameters. So this is a side view of us or a human looking into some typical head-mounted display. Most current generation VR displays follow this format. So a couple parameters are important. We have the height of the microdisplay defined as h prime. The distance between the lens and the microdisplay is defined as d prime here. And then we also have some eye relief, which is the distance between, the lens and the eye. We can't actually push our eye directly against the optic, right? We need to, well, that wouldn't be very comfortable. I don't want anything touching my eye. We need to give it a little bit of room, and then we call that the eye relief. So this virtual image that I was saying, this magnification of the microdisplay, its parameters are defined by h, and the distance between this virtual image and the lens is defined by d. And what these two parameters are actually pretty simply defined by using the Gaussian thin lens formula. So if we use this and assume that the lens that we're using can be modeled approximately as a thin lens, we can use this relatively simple equation to determine the distance to this virtual image from the parameters, physical parameters of the display that we have. Now, the size of the display of the virtual image h is defined by this magnification factor, which is again related to this Gaussian thin lens formula. So now that we have a rough understanding of the image formation of a head-mounted display, well, when we get to stereo rendering specifically, we actually only have to modify two matrices in the entire pipeline. We only have to change the view matrix and the projection matrix. So the additional thing, so essentially if you have some scene defined and you want to go from just a single monocular view, just rendering out one image, to rendering out a stereo image, it actually is quite easy. And many different engines now actually support just kind of toggling, I want to do stereo or not, and it'll set up something very quickly. So the idea is you just need to render two images out now, one for each eye, and the rendering process for each eye will have a different view matrix and a different projection matrix, but defining the entire scene and everything else is exactly the same as you would with just defining something that you would render once to just a computer screen, for example. So the typical method of doing this is you start out with a blank screen, you render out the left eye, for example, then you render out the right eye, and then you can actually see the image. So you have to perform two rendering passes. So, okay, so let's start with defining how do we adjust the view matrix to perform this rendering. So the view matrix, as I said earlier, adjusts the position of the camera in this world space to define the viewpoint at which we want to see the scene that we've built. Here's some simple scene that we have. So this is one viewpoint. We can change it to be over here. I don't really like that one. This one seems good because we can see all the objects at once. But we don't have only, we're not using, when we look into the real world, we don't have one camera, we have two cameras. If you think of our eyes as cameras, we have two of them. So we can't just use, like I said, this one projection. We need to have actually show the scene or create the image from two different locations. So how do we go about doing this? Well, the distance between our two eyes is referred to as the interpupillary distance or interocular distance. And this is somewhere typically between 60 millimeters and 65 millimeters. And the camera that we've defined earlier, this viewpoint that we liked, right? We define it, the view matrix, as this translation and rotation that we have on the bottom there. Well, after performing this view transform, we have the origin of that space, of the view space, to be at the center of the camera with the z-axis, the positive z-axis pointing behind the camera. So actually the camera is looking down the negative z-axis. And the x-axis in this image is pointing up, but it's actually pointing to the right. So to define the two views that the eyes would see, we just need to add an additional translation, right? One for each eye. So we can do this by just adding another translation into the fold after we multiply by the view matrix and transforming and translating the view from each eye by half of the IPD. Now, of course, when we look into a microdisplay or into one of these HMDs, we're looking through some glass optics, and depending on the HMD itself, we can either adjust the distance between the lenses, or we can't. And the reason we would like to adjust the distance between the lenses is because everyone has a slightly different interpupillary distance. So if you look at the HTC Vive or the Oculus Rift, you can adjust the knob and you can space the lenses apart to account for every person's individual interpupillary distance. Unfortunately, the head-mounted display that we have, because it is, $20? It doesn't have this feature, and it fixes the lenses in one location. So actually, instead of having the view transform be adjusted for each person's IPD, we have it set to the distance between the lenses themselves, and this makes it so, this is important later when we define the projection matrices, just as a note. And the effect this has on people that have different IPDs than that of the spacing between the lenses, it essentially forces our eyes to verge in a little bit closer, so essentially shifts in the entire virtual world slightly. It's typically not that, it's technically perceptually incorrect, but not super, super noticeable. So if we move on to the projection matrix now, this is this view that I was defining a perspective transform or projection transform as a view frustum, which is defining essentially the top, bottom, left, and right coordinates of the intersection of this frustum with some near clipping plane or some plane in front of the camera. So if we go back to this projection of the image formation model from the side view, if we get rid of all of this junk, we'll see that if the eye or the lens is placed at the center of the display, we have a symmetric viewing frustum. So from the side view anyway, we have the eye being placed at the center of the display, and it'll see the same number of pixels above and below its center. So it's actually quite easy to define the top and bottom coordinates of our viewing frustum that we're looking for. We can define a near clipping plane essentially wherever we choose. This is defined by the z near distance here. And we're looking for these top and bottom coordinates to define our viewing frustum. So just with similar triangles, we can define it in this manner by knowing the height of the virtual image, the eye relief of the eye to the lenses, and the distance of the virtual image to the lenses. And we can do this by following the equations for D and H that we had on the previous slide. So again, we have all of these equations up on our course notes, so you can just follow these from our E267 course notes online. So this is the easier of the two steps. If we look from the top view now, things get a little bit more complicated. So our eyes, we have two of them, so we have to have two lenses, but these lenses aren't guaranteed to actually be placed at the center of each display that the eye sees, or each part of the display that the eye sees. So we actually have to generate a slightly non-symmetric viewing frustum from the top. So if we just look at the left eye, remember that essentially when we look through this display, we're looking through essentially a window into our 3D environment. So because the lens may not be directly aligned with the display, the lens describes the center of projection, and the display describes kind of the window through which we're looking. We have to define this asymmetric viewing frustum. So if we, so essentially what that means is the lens isn't aligned with the center of the display, so the pixels to the right of the display, or distance W1, will be greater than or less than W2, which is the distance to the left of the display, or left of the center of the display. We can define these parameters by these equations, so it's just a magnification of half of the IPD, and essentially the half of the display minus that distance. So generating the actual frustum itself, we have to intersect these points with the near clipping plane, and we can do this. So we're essentially looking for these two parameters, the right and left parameters of the viewing frustum. And we can do this by just, again, using similar triangles with these two equations. Again, these are all online, so I don't expect you to remember them. And we can do the same thing for the right eye. Again, defining W1 and W2, and then finding the corresponding right and left parameters for the viewing frustum. So for this, it's really important you notice that we need to know a lot of physical parameters about the display itself. So this projection, defining these projection matrices is very intertwined with the specific hardware that you have, the focal length of the lenses, the distance between the lens and the screen. And we have all of those defined here for the ViewMaster starter pack that we have. The focal length of the lenses are 45 millimeters, the lens diameters are 25 millimeters. All these are very important for defining these matrices correctly so that you have a pleasant viewing experience. And you also need to know the dimensions of the LCD panel, which we have provided here. So the image formation, we have to use the formulas that we've just defined to compute this perspective matrix that we can just plop in with our three function make perspective, which just exactly takes what we just calculated, the left, right, top, and bottom parameters, as well as our near and far clipping planes, and we can define our camera with just a look at function. And that's essentially all you need to actually render stereo images on an HMD. Just following these simple equations, you can render your own stereo content on one of these ViewMaster starter packs that we've just described earlier in the course. So this becomes more complicated once you have more complex optics, especially if you have freeform optics or off-axis optical configurations. This doesn't apply to those types of systems. This is essentially defining the image formation model for simple magnifier displays, which current VR displays all follow. You can use ray tracing or some other nonlinear mapping to generate this view frustum or generate the mapping of your display to what you end up perceiving at the pupil plane where we end up perceiving the image. Those are all more computationally challenging and sensitive to very precise calibration. Our HMD and most magnifier-based systems, like I said, follow our derivations that we showed here. So the last thing I'm going to talk about in this session is lens distortion. It's correcting for the optical aberrations that are induced by having these kind of high-power lenses that we look through and that we magnify the image with. So all lenses introduce some sort of image distortion, either through chromatic aberrations or artifacts, and we need to correct them the best we can in software. We can actually do quite a lot in software. So if we were to just display something on the screen and look through this lens, we can see that these straight lines that we're expecting to see, especially near the edges of the lens, start being curved, not straight anymore. So this is called a type of pincushion distortion that we would like to correct for in software. And we can do this by introducing the kind of the opposite distortion, which is the barrel distortion. So essentially now if we kind of pre-warp the images on the display itself, if we kind of bend the lines the other way when it passes through this pincushion distortion introduced through with the optical system, on the other side we'll perceive straight lines once again. And the pincushion distortion, as I said, is the optical distortion, and the barrel distortion is what we introduce digitally in software. And you can see that here. So the display shows this classical kind of warped images that you consistently see whenever you look at, if you Google VR images or VR display, you'll see kind of a black background with kind of these like weird warped images left and right, and that's essentially due to this lens distortion. That's the exact reason we have those weird shapes whenever we look at the display itself and not through the lenses. But when you look at the images through lenses, we'll see corrected images with straight lines being straight. So how do we implement this? This barrel distortion. If we have XU and YU be an undistorted point indicated by these blue dots, we can compute its corresponding barrel distortion by defining some center. So the center dot, the center red dot would be XC and YC. That's the center of the distortion, and that corresponds to the center of the lens. And we can calculate the barrel distortion by essentially this equation here, which is just a truncated Taylor expansion. So just with this simple equation, essentially it's a distortion that is a function of the radial distance from any given point to the center of the lens. And we can compute this very efficiently in various ways that I'll describe in a little bit. Now, the center is assumed to be at the center point of the optical axis, not necessarily on not the center of the screen. So you have to calibrate and figure out the center of the lens on the screen itself to be able to define this and do this correctly. And the distortion is radially symmetric around its center point. It's actually quite easy to get confused when you start implementing this. It's very important to take note of this. So as I said before, the center of the point is essentially if you just drop a beam through the center of the lens, that pixel on the screen that will define your center of the lens distortion. And as an example, if we see this image where we don't have any lens distortion on the left side, if we look through the lens, we'll start seeing these warped images. You can see the curve, the straight line is curving at the bottom. But if we apply the lens distortion correction, we start seeing straight lines becoming straight again. So how do we go about implementing this? The end goal effectively is to move the pixels around to correct for this optical aberration by introducing a barrel distortion. Well, we have two parts in the pipeline where we can do this, and essentially it's the two parts that are programmable. So we can either do this in the Vertex processor or in the fragment processor. So there's two ways to do this, like I said, the fragment shader and in the Vertex shader. In the fragment shader, we can essentially go through the entire rendering pipeline for each eye, render this into a frame buffer object, and then apply a per fragment operation following those exact equations that I showed, and just move the pixels around using this barrel distortion operations. It's very simple, and you essentially apply this on a per fragment basis. Now, the problem with this is that you have to apply this on a per fragment basis. So as your displays start becoming higher and higher resolution, you have to start applying more and more of these operations every single time you display a frame, because this is applied at every frame, right? So to reduce some of the computation needed here, we can actually perform this in the Vertex processor and take advantage of the rasterization process itself, the interpolation process. So what we can do is we can, instead of projecting our texture or the image that we end up rendering onto just a rectangle and then warping that in our fragment shader, we can directly warp the images that we display by pre-warping a sparse mesh, and then just take advantage of the interpolation that happens in the rasterizer to essentially interpolate kind of batches of pixels simultaneously. So if you have a very, very sparse mesh, you start getting certain artifacts, but actually even with like a 20 by 40 mesh, the artifacts become imperceivable, and you can speed up the rendering, the number of computations significantly this way. So I'm not going to go into the details of how specifically to implement them, but these are two well-known methods for implementing lens distortion. And with that, I'll conclude this section of the talk anyway. And if you would like to have more information on everything I've talked about here, I'll direct you to the course that I've been mentioning earlier, and you can go to of course, look at the book Fundamentals of Computer Graphics for more basic computer pipeline information. So with that, I'm going to hand it over to Hayato to show you a demo of what I've just been talking about here.
Okay, so this is the first homework where you are going to learn the transformation with matrices. You are going to start with non-interactive scene, and after completing the homework, you would be able to control the model matrix to rotate the teapot, and also you can control the view matrix, and also you can control the projection matrix. Of course, these kind of operations can be done in 3JS without knowing the matrix, but you are forced to implement it by yourself. And in the second homework, you are going to implement the shaders that Robert has explained, like grow shader and also phone shader. You are going to implement different shaders on different teapots, and after completing the homework, you'd be able to control the position of light and also add the light. You can also add the directional light, and you can still control the teapot. And finally, you are going to render the stereo. You are going to perform stereo rendering and start using the head-mount display. As we have been explaining, This head-mount display has a high-resolution display inside. And you are going to connect it to your laptop or desktop computer by using HDMI cable. And just use a full screen mode of your browser to render the scene. And we are going to ask you to implement the lens and distortion shader that Robert has explained. And by using the grid scene and also the lens and distortion mode, and by controlling the lens parameter, you are going to try to make this grid flat or straight line while you are using the head-mount display. And I am going to pass to Gordon to explain about the orientation tracking and position tracking.
Great, thanks so much. So far we've learned all about computer graphics, and many of you probably know these parts already. What we've done for this class is basically ported the conventional graphics pipeline in a regular course from OpenGL to WebGL, and students have been using that very successfully. Remember that in the class we have students from the business school, from all kinds of engineering departments, and not everybody is as good in C++ programming as all of us, but WebGL really makes it easy for us to do all of these things. And we now know also how to do things like stereo rendering, lens distortion. So the code is online. If we can't find it, feel free to send us an email. We don't want to put the solution for next time online, so if you send us an email, we'll send you all the solutions as well. So in this part of the course, we'd like to talk about the next step, basically, after you have the stereo rendering implemented on your head-mounted display, which is basically incorporate tracking so that we can do orientation tracking and also positional tracking. Let's start with the little story here. What we see here is the Polynesian migration. So CVPR, the conference, was last week on Hawaii, and I was always curious how people actually managed to first get there, right? The Hawaiians must have gotten there. There was a period of about 3,000 years over which the Polynesians migrated from Asia through all these islands in the Pacific all the way to Hawaii, for example, as well. So they didn't have GPS. They didn't have any sophisticated technology, basically just a raft. How do you think they managed to get there? Any guesses? I haven't actually seen the movie yet. Oh my God. Okay. Well, you basically have to use any cue that you can get, right? So waves, wind, birds in the sky, anything that can be helpful to help you navigate, the stars, of course, right, is useful. And using the information from all of these cues and fusing them together into getting a robust kind of a way to navigate is the key, I think, for not going into the wrong direction here for too long. And the same is true for tracking also. Tracking is a multimodal thing. We are going to use multiple different sensors, and we're going to try to fuse the benefits of all of those sensors together to overcome their respective limitations. And that's kind of the core message for the tracking. So what we'll be talking about in the next little while is the coordinate systems that are important for orientation tracking, positional tracking. We're going to give you an overview of inertial measurement units like gyroscopes, accelerometers, and magnetometers. We'll talk about how we do the orientation tracking on IMUs. This is largely based on Steve Laval's work that he did originally at Oculus in the DK1. It's published in a paper from 2014. There's also a textbook by him. We'll talk about the vArduino and how we implemented it with our open source hardware. And then I'll talk about pose tracking also, so positional tracking. But first, let's do orientation tracking. So orientation tracking is useful for many things like controllers, but let's just think about it as the headset. We have an IMU on the headset. We look up. We want the virtual world to transform down so that we see a natural response of the computer graphics content with respect to our physical head motion. So the goal is to track the orientation of the device or our head with respect to the world. So it's really important to understand that reference frame, the world, right? So what is the world? From the perspective of the sensor, of the inertial sensor, the world is, gravity going down. The world is a magnetic field pointing to the North Pole, and that's going to be our reference for the inertial sensors. So the device frame or body frame is going to be in the local coordinate system of the vArduino or the IMU, and the inertial frame is going to be the world frame. That's the reference frame. And what we'll be doing is representing rotations using Euler angles for starters. We don't have enough time to really go into quaternions. I'll give you a little outlook, and you can find all the course notes that also include quaternions on the website if you're interested. But we'll mostly work with Euler angles, and I'll tell you in a second what that really means. Orientation of the IMU is tracked from the measurements of the IMU in its local coordinate system, but what we want to track is the yaw pitch roll, so the rotation around x, y, and z axis in these world coordinates. So for example, a pitch of 90 degrees means I'm going to be looking up by 90 degrees, which means that correspondingly the world that I'm rendering should rotate downwards so that it just matches my natural transition, right? Okay, so we looked at how mathematically we can describe that using the graphics pipeline. Robert explained that how a vertex, for example, in its own local coordinate system can be transformed into the world using the model matrix, then into the view matrix using into the view space by using the view matrix, and then finally the projection matrix. So that's the model matrix, view matrix, projection matrix, and at the end we're in clip space. So the view matrix can be further decomposed into a rotational part and a transitional part. What we're going to be trying to do with the orientation tracking with the IMU is estimate the parameters of the user for this rotational part of the view matrix. Right? Think about a virtual camera being attached to the head of you physically, and as you rotate around, that's exactly what should be happening in OpenGL and computer graphics. So the sensors will give us the parameters for these rotations. And then the positional tracking, as I move my head and I want to get this motion parallax and look around an object, that's going to come from the positional tracking, and that's going to be defining our translational part of the view matrix. But it's all about estimating these parameters of the view matrix. So it's really important to understand the rest of the graphics pipeline if you want to be integrating these track data into the graphics pipeline. Again, as Robert already explained, if you have stereo rendering, there's another translational part just by the interpupillary distance to get the stereo cues correctly. So here's something very important. The world coordinates here are going to be on the right-hand side of the rotation matrix. As we apply the rotation matrix that we estimate from IMU, we're going to be in the sensor or body frame. And as I said, we're going to be using Euler angles. Euler angles means we're going to have one angle per axis, so rotation around x-axis, rotation around y-axis, rotation around z-axis. I find it particularly useful to just use my right hand for the OpenGL coordinate system, right? The thumb represents the x-axis, y is up, z comes out of the screen towards you. That's exactly this. And then I can think about pitch, yaw, and roll, like these three rotations, and we're going to have to define them in a particular order. In this case, we're going to just use roll, pitch, yaw. So Euler angles are very easy to work with, but they're usually a terrible idea to be used for orientation tracking in more than one dimension. So we're going to look at one-dimensional tracking, two-dimensional tracking. I'll give you an outlook of quaternions that are usually being used for 3D tracking. It just gets a little bit too complicated, so we can't really cover it in the short amount of time we have right here. So one thing that is very important that Robert already mentioned is that rotations are not commutative. So if you define the order of rotations, that's it. We can't change it, and you may run into trouble for certain configurations, which is known as gimbal lock. But for now, I'd like to give you an overview of inertial measurement units and what these sensors are and what they actually measure before we go into how to process that raw data and get the orientation back. So inertial sensors measure different things. Gyroscopes, for example, measure angular velocity. And we're going to denote the angular velocity measured by a device as the omega tilde here. And that's usually measured in degrees per second or radians per second. The accelerometer measures linear acceleration. And we'll denote all these measurements with a little tilde because the tilde includes measurement noise and other things. Whereas the actual value that we don't know, the ground truth, would be the same value without the tilde. And then the magnetometer measures the strength of the magnetic field in microtesla and Gauss. All these measurements are taken in the local coordinate system of the IMU, right? So keep that in mind. We have to estimate the orientation of the IMU with respect to the world, but we just measure everything in the local coordinate frame of the IMU. So let's talk a little bit more about gyroscopes. Gyroscopes have been around for, well, almost 100 years now. They've been used in rockets and pretty much anything that moves back in the day. And now we have, of course, MEMS devices, so micro electromechanical systems. These are very small scale, low cost, low latency devices that are, just great. And every single cell phone of you has an IMU in it. That's what makes the screen flip when you rotate your phone. And what they measure is the Coriolis force. As you rotate something, there's a force going outwards, and we can build a little MEMS device that will measure that. So that's really what enables mass fabrication and low cost. Gyroscope measures angular velocity, and we're going to use the following gyro model. The measurements are a sum of the true angular velocity, omega, plus some bias. And the bias I'll talk about in a second, but plus some additive Gaussian noise. So Gaussian measurement noise is something that is quite common for all sensors, but the bias is something that is a little bit unique here. So usually gyroscopes come actually as a 3-axis gyro. So you're going to have 3 gyros mounted on the same chip, and they're all orthogonal to each other. Each of the gyros will measure the angular velocity in one direction. So think about the inertial organ in the ear, the vestibular system. We have these 3 semicircular canals. The IMU is going to be very similar where we measure the rotation on 3 different axes. And we're going to assume for the rest of this course that there's no crosstalk between them. So they're perfectly orthogonal to each other. The bias is actually temperature dependent. It's a factor that changes the measurements and distorts it by, you can think about it as a scalar, but it actually changes slowly over time. But we're just going to ignore that and assume that the bias is going to be a constant value that we can calibrate in a pre-processing step. So now, once we measure angular velocity, how do we actually get the angle back? So how do we go from the first derivative of a value to the actual value? We're going to have to integrate, and that's an ODE, and we're going to use the Taylor expansion for that. So on the left-hand side, we have the angle theta. That's the quantity we want to track. We want to track it over time from one time step to another. We actually know or have some kind of an estimate of what it was in the last time step, and then we just need to know the derivative of the angle with respect to time, which is exactly the angular velocity times the time step that's in between. There's some error term because this is a truncated Taylor expansion, so depending on the time step in between the measurements, you're going to be drifting away from your actual measurements. Right? So the quantity we want to track is the actual angle. The measurement that we have is the angular velocity, and we can use the microcontroller or whatever device we're using to pull these measurements to also measure the time step in between individual measurements. But there's always going to be some approximation error here. So that's something that we can't get rid of. If we only use a gyro to track the angle, that's also known as dead reckoning. It works very well for linear motion if there's no noise and no bias in the system, but these are unrealistic conditions. So with the gyro only, it's a very nice device, but your true measurements are going to be drifting off away from the true measurements. Even if you have the right initial condition, even if you have no measurements in your noise, and even if the time step between measurements is very short, you're still going to drift off away from the true measurements. So the gyro measurements are very accurate in the short term, but they become unreliable in the longer run due to the drift. And I like to show this map of one of my favorite games that I used to play back in the day. It's called Pirates. Navigate through the Caribbean and conquer a bunch of islands here. So think about what people had for navigation back then on a ship. You have a compass that points north, and you can maybe measure your velocity every once in a while. So you want to get from the blue point to some island, but you can only measure the velocity every once in a while. So what's going to happen is that over time, this approximation of a curved trajectory with piecewise linear things is going to drift away from your actual target, and you're going to just end up on a different island, right? So this is the same effect. It's this drift, and there's nothing you can do about it if you have discrete measurements in time. All right, so let's look at accelerometers because they're slightly different, and they will be able to compensate for this drift. Accelerometers measure linear acceleration, and acceleration is the second derivative, right? But in this case, it's linear, not angular. So the measured linear acceleration A tilde is going to be the sum of the gravity, because we're going to hold up the IMU with either our head or our hand or something else. So there's already a force acting on it. Because gravity will pull it down. Actually, the force that we're applying to it is going to point up. Right? Just by holding it static, we're applying a force that points up, because if we didn't, it would just fall down. Okay, so then AL is the linear acceleration, any external force, like any motion that we apply to the device, plus some measurement noise. So without any motion, and let's say without any noise, the accelerometer values should point up in world space and with 9.81 meters per square second. So that's gravity, basically, or 1g. As soon as we have some kind of motion, then we're going to have these external forces in there too, and which makes it a little bit challenging. So here's a micrograph of a MEMS device, a MEMS accelerometer that is very similar to the gyro, it's just slightly different. Here's a nice animation of what it actually does. So there's going to be a proof mass that's fixed on it, and there's going to be one part that moves as you apply these forces, and the capacitance between these chambers will actually change, and that's what the device will read out and report as values. So that's how you read out the different motions. The advantage of accelerometers is that, again, on average, they point up. And even though there may be noise in every single measurement that you take, over time, it will still point up, because gravity is going to be our absolute reference frame that's not going to change, at least not over the lifetime of the application that we're going to be running. So the individual measurements are going to be noisy, but on average, it's going to point up. Even if I apply an external force, that's only going to act on the device for a little while, and on average, it's still going to point up. So that's very important to have this global reference frame, and that's something that we don't have with the gyro. The gyro always takes these relative measurements of angular velocity, so after a little while we lose all notion of a global reference point. But the accelerometer will provide exactly that. So they're complementary to the gyro measurements, and the best sensor fusion approach, of course, takes the good parts of two different things and brings it together, and that's exactly what we're going to be doing. So fusing gyro and accelerometer measurements is known as 6 degree of freedom sensor fusion, and we can correct the tilt with that, so the pitch and the roll. But we don't have any notion of heading or yaw, the rotation around the y-axis. We don't know that. So we can't correct everything. That would be 9 degree of freedom sensor fusion. So let's start out with a really simple example just to understand what's going on here and what's intuitively happening. So let's live in flatland for a second. Anybody read that book? We live in a flat world. It's not three-dimensional. It's really just x and y. In this case, we're going to have a gyro that tracks the one-dimensional angle, or in this case, angular velocity, but we want the angle theta. And we're going to have a two-axis accelerometer. So it's going to measure acceleration in x and y. And the goal is to understand the 6 degree of freedom sensor fusion. So again, we take the gyro measurement. It's just a single value omega tilde. We multiply it by the time step delta t, and we add it to our last estimate of the gyro, and that's how we're going to integrate our gyro measurements. We can get delta t from the microcontroller, let's say the Arduino that we're using, and we have to set the initial value to something. For example, we could set the first gyro measurement or the first angle to 0, or we could use the initial accelerometer reading or something else, some initial guess, and then we're going to track over time. Again, over time, it'll drift away from the actual angle where we are at. The accelerometer will measure, ideally on average at least, the up vector pointing up in world space, but the measurements we're taking are in local device coordinates. So the blue vector on the right represents the up vector from the IMU, but the measurements we're taking are with respect to the local x and y axis in the coordinate system of the IMU, so that these are the red axes. But we want that vector with respect to the world axis. So we can get that by simply dividing the x and y measurements here of the accelerometer and compute the inverse tangent. It's always a bad idea to divide one value over another if you can't control that it's never 0. So in practice, you would want to use the A10-2 function, which is provided by pretty much all programming languages that also handles the division by 0 and the appropriate signs. But using the simple A10 function, we can get the world vector pointing up, and that gives us the angle also, theta. So now the biggest problem is going to be noise from the measurements, and the idea for the sensor fusion is now that the accelerometer values are going to be noisy, the gyro measurements are going to be drifting away, so we want to apply a low-pass filter to the gyro No, we want to apply a high-pass filter to the gyro to keep the short-term information. We want to apply a low-pass filter to the accelerometer to filter out the noise, and then we want to combine these measurements. And the easiest way of doing that is called a complementary filter. It sounds fancy, but it's really just a linear interpolation between these two values. So our tracked angle on the left, theta t, will be the integrated gyro measurements on the left plus the estimated rotation angle from the accelerometer, and we're just going to apply a linear interpolation factor alpha with respect to that. And it's as simple as that, gives us no drift and no noise over time. Potentially a tiny little amount of latency in these measurements. So Hayato is going to show us a live demo. Here's just a video that I captured beforehand. You can see the live stream out of the Arduino. What you'll see is that the red line is going to be the noisy accelerometer measurements. So you can already see that they're actually very noisy locally. But over time, they provide a stable reference frame. This is just a 1D angle, right? I'm just tracking the theta angle. This is in this case, it's the roll. The gyro is going to be very smooth, but over time, the gyro is going to drift away. So here's a screenshot after a little while. Gyro looks great, but is just off. And the accelerometer is very noisy. In this case, accelerometer is the orange one. The complementary filter looks in shape very similar to the gyro, but it is it's globally shifted to the position of the accelerometer. So this works really well. Okay, that was the flatland example. Let's take a look at 3 dimensions. And let's start out with only the accelerometer. So moving away from the sensor fusion, let's just understand how we get pitch and roll from the accelerometer. And in this case, we want to have a 3D accelerometer pointing up, forward, and right, and we want to estimate the pitch and roll. And that those two angles together are known as the tilt, right? So tilt is roll and pitch, but it doesn't have any information about the yaw. So this may seem a little bit complicated, but the intuition is actually quite easy. It's the same thing that we just used. On average, the accelerometer value should point up in the world coordinate. So that means the vector 0, 1, 0, which represents the up vector in global space, rotated into the local coordinate system of the IMU should be basically equal to our normalized measurements. So we're going to use the A tilde and normalize it by length. And the unknown angles, theta x, theta y, theta z, should be such that this up vector rotated into the local device coordinate equals these angles. We don't know the angles. That's what we're trying to figure out. We're going to use our definition of the rotation matrices that Robert introduced us to earlier. We just write out these 3x3 matrices in this case because we don't have a translation. We can get away with 3x3 matrices. We multiply all of them out. And basically what we'll see is that the angles theta x, theta z are related to the normalized accelerometer measurements here. There's no dependence on theta y. It just fell out of the equations. And theta y, again, is the heading. So there's no way we can estimate the yaw or the heading from these measurements. But now that we know how angles should be related to the accelerometer, we can simply divide the normalized measurement x and y. That should give us the tangent. And again, we're going to use the atan2 function to compute our angle theta z. What we're not going to be doing is use the third measurement and directly relate it to theta x. We're always going to divide these to be getting the right signs here. Because if you just use the sign directly, there are 2 possible solutions. We're going to disambiguate this. So we need always to combine 2 of these values. So this is the roll. Pitch is right here. We're going to divide az over square root of ax square plus ay square. You can see that on the right, a bunch of terms fall out. It ends up being a tangent again. And in this case, we're just going to relate it again with the atan2 function and combine these accelerometer measurements to get the pitch in this case. So that's pretty much it. Very simple equation to get pitch and roll from 3-dimensional accelerometer values. If you didn't follow, don't worry. All of this has extensive course notes also on the website that you can read up in detail after the fact. So the magnetometer is going to be measuring the magnetic field. Magnetic field is with respect to the Earth again. We're going to have 3 orthogonal axes, so the magnetometer value is going to be a 3-dimensional compass pointing north. That would actually change depending on the latitude and longitude on the surface of the planet. If you're directly on the North Pole, it would point down. If you're on the equator or somewhere close by, it'll point north. But it's also going to point down a little bit. So you would have to know kind of approximately where you are if you want to be able to use these values reliably. The magnetometers are complementary to the accelerometer because they help us figure out what the yaw is, because they always point north, at least in our latitudes. The problem is that the magnetic field is quite affected by metal distortions of the magnetic field. Any kind of electronics that are around the magnetometer will distort the magnetic field, and we're going to get unreliable measurements from the magnetometer unless we pre-calibrate it in the particular environment. So even if you take it into a different room, there's a bunch of computers create a magnetic field, your measurements may be unreliable. So you can do all of this, and students do that in the course project, but we don't really do it as a homework because it's a little bit too complicated. So we mostly implement the 6DOF tracking with the accelerometer and the gyro, but you can find more information online. So as I said, in 3D, you want to do orientation tracking with quaternions. For those of you who've worked in computer graphics for a little while, especially in animation, you're probably very familiar with quaternions. For those of you who've never heard this term before, it's quite scary. So quaternions give us a nice set of tools of mathematical algebra that allow us to represent rotations in a different way, different from Euler angles. They allow us to represent rotations using an axis angle representation. And that will help us overcome some of the limitations of Euler angles, which are obvious in computer animation when you have two different orientations or rotations for different keyframes in animation. As you interpolate between these, you can't really just interpolate the angles. That doesn't work. You'll get unexpected results. And the same happens for integration in 3D for the orientation tracking. So you need a better representation for orientation if you don't want to run into trouble. And that is axis angle representation. So in this case, we're not going to rotate around the x-axis, y-axis, z-axis, but we're just going to rotate around some arbitrary axis that we define in space. Okay? So axis angle means we have one angle and one three-dimensional axis, and we're going to rotate around that. So the axis will usually be normalized. And that's quite a common representation for orientations in computer graphics. The quaternions give us a nice tool set that allow us to work with axis angle representation because now we can interpolate between them, we can add them, we can multiply them. We have all these algebraic tools that are well defined for quaternions, and we're just going to use them as a container for this axis angle representation of rotations. And a quaternion looks funky. It has 4 values, QW, QX, QY, QZ, and it's kind of like a complex number that has a real part and an imaginary part. But in this case, we're going to have one real part, which is QW, and 3 different imaginary parts. So that's why we have this set of 4 values. And the imaginary units here, or the fundamental quaternion units, I, J, K, they're all different. But again, square root of them is going to be -1, or if you square them, it's going to be -1. If you combine them in different ways, you can read up the algebra down there. So they're different, but you can use them to define operations like multiplications and other things. So it's a powerful set of algebra. You can try to understand it and philosophize about what it really means, and I'll leave that as a homework to you. But if you just implement it, it usually works quite well also. So if we have an axis and an angle, so theta and v, we can convert that to a quaternion using this equation here. So the scalar part, QW, is just going to be cosine theta over 2, and then we're going to combine the different axis elements and the angle for the other 3 imaginary units of the quaternion. Just as a side note, any quaternion that represents a rotation is going to have unit length, so its norm is 1. But there are other types of quaternions too that represent a point in 3D or a vector in 3D. And those are called vector quaternions. And those have a scalar value of 0, and they don't have to be normalized at all. And so now we can take 3D points or vectors, and we can rotate them, just like we did with the 4x4 or 3x3 matrices earlier, using quaternion algebra. And that's a little bit different. It's more like a polynomial that we're going to combine. So we don't have enough time to go into the details here. If you're interested in quaternions, there's a lot of computer graphics literature out there that explains in detail. I also wrote course notes on the website where you can read up in detail how to do that. But the basic steps for quaternion-based orientation tracking are very similar to what we discussed earlier. You're going to take these measurements with the gyro and the accelerometer, you're going to convert these into quaternions, and then you're going to do some quaternion algebra to interpolate between these values to stabilize the tilt from the gyro measurements. So the idea is the same, just the mathematical operations are slightly different. And you're going to do all of this on the Arduino and then stream the resulting quaternion that represents the orientation of the head or the IMU to the application in OpenGL. So one little side note, and I hope this is my artistic skills are reasonably clear here. We don't actually rotate, if we have the head-mounted display and the IMU on the headset, we don't actually rotate around our IMU, right? We're not going to rotate around this center of rotation. Most of the time when we look around in a VR scene, we're going to rotate around the base of our neck. So we can use this head and neck model if we have a reasonable approximation of what the distance between the IMU and the base of the neck and the length of the neck and the head is, and we can incorporate this into the rendering and actually define the center of rotation to be the base of the neck. And that's usually called the head and neck model. What that allows you to do is it gives you a little bit of motion parallax even if you don't have positional tracking. So if you rotate the IMU this way, you know that you didn't rotate your head this way, you actually probably rotated your head this way. So there's a little bit of motion parallax that you can get out of just using the IMU. And it can be quite effective. Okay? So once we have the orientation, we're going to bake that into our view matrix, as we said earlier. So now we implement the orientation tracking with the VArduino, and I'll show you what IMU we're using in the VArduino. We have a 9-degree of freedom IMU, the InventSense MPU 9250. So that's an updated model, what was in the Oculus DK2. Well, it's mostly updated because it uses the magnetometer, which we don't end up using all that much. But the magnetometer is still interesting for, doing metal-based interaction. You want to add a button like the original Google Cardboard, things like that. So it can be useful. So it has 3-axis gyro, 3-axis accelerometer, 3-axis magnetometer, all in one chip. And you can interface it with I2C. So that's a serial bus from the Arduino. So if you don't know what I2C is, it's the easiest way of interfacing anything with an Arduino, pretty much. So we have an Arduino, in this case a Metro Mini. That's what we used last year in the course. We switched to the Teensy this year. But you can connect the IMU with just 2 wires, basically, in addition to power and ground. And these IMUs usually come with a breakout board, so you don't need to do much. You just plug a cable in, and it just runs out of the box. So it couldn't be simpler than that. And then from your computer, you can just plug a USB cable into the Arduino and read out and stream out the values through the USB port, through the serial port. So let's look at the sensors that are on the IMU here. We have gyro, accelerometer, magnetometer. The magnetometer is actually referred to a third-party device in the spec sheet. So InventSense only makes the accelerometer and the gyro. The magnetometer is from a different company. Each of these take analog measurements that are then digitized by an analog to digital converter. And these ADCs, for each of the 9 sensors, have 16 bits. So you're going to get signed integer values that are in the range between 2 to the 15 minus 1 to 2 to the 15, right? So that's the number of values you can represent. So what you can do with these sensors is you can actually set them up with a different range. What that means is, for example, the accelerometer can have a maximum range of plus minus 16 G. That means it can measure a large range, but with the 16 bits that it has to represent all these values, it's going to be not as precise as if you set the range to something smaller. So we usually pre-configure it with the largest range, and then we don't care so much about the precision, but that's something to keep in mind. All right, so the raw sensor value is just divided by 2 to the 15 minus 1, multiplied by the max range, and that gives you a metric value of then, degrees per second or radians per second for the gyro, or G, or meters per square second for the accelerometer, and that's pretty much it. The coordinate systems for the gyro accelerometer, for the magnetometer, are slightly different. Gyro accelerometer uses a right-handed coordinate system similar to OpenGL, so it's perfectly compatible. The magnetometer uses a left-handed coordinate system, so you need to convert these values first. And again, it's very simple to connect these two. You're just going to connect power and ground. These operate at 3.3 volts, and you're going to connect the clock and the data line for the I2C signal. So really, it's just 2 wires. And that's pretty much it. So then you connect your USB cable and you can read out the data. We already implemented all of this on the VArduino. You can remove the Teensy and the IMU from that, or you can plug it in. It's just a couple of headers. These are connected through the PCB underneath. It's a very simple 2-layer PCB, and we have a couple of additional GPIO pins on the left. So that's pretty much it for orientation tracking. So what we talked about was different coordinate system, local coordinate system versus inertial or global coordinate system. We want to be able to track the orientation of the IMU with respect to the global system. Gyro integration, we talked about gyros, accelerometers, magnetometers. Gyro integration is known as dead reckoning. Orientation tracking flatland, 3D accelerometer, and we gave you a hint of what may be necessary to implement all of this with quaternions in 3D. And you can use the vArduino as an experimental platform, or you can just use any IMU and Arduino or other microcontrollers. So for the rest of the session, I want to talk a little bit about pose tracking. So that's positional tracking because it adds quite a lot, but it's not straightforward. So the IMU part is well explored. Many of you have probably worked with IMUs before. If you haven't, you have now all the information that you need. But pose tracking is something that's not as straightforward. So we'll talk a little bit about what positional tracking or pose tracking is. We'll look specifically at HTC Vive's Lighthouse technology, which is a really good low latency tracking system. And we kind of try to reverse engineer that a little bit and bring that experience to the students on the vArduino. So we'll show you how to implement it, and we'll go through the math a little bit. So we'll talk about homographies, which is the easiest method of estimating the 3D position and orientation from the Lighthouse measurements on the Arduino. In the class, we also talk about nonlinear optimization for that. We're going to skip that here, but the course notes are online if you're interested. Everything is already implemented, works quite well. So in this case, the goal is to track the position, X, Y, Z, and potentially also the orientation of a controller, a headset, or something else. The pose, in this case, is going to be 3D position and orientation. I can tell you right now that the orientation from this tracking is going to be much more noisy than from the IMU. So again, you would want to do some kind of a sensor fusion between the pose estimation from the photodiodes and the IMU. We don't do that right now. But you could just pick the orientation from here and the position from here, put the two together, and that works pretty well. Okay, so for positional tracking, people usually talk about two different approaches. One's called inside-out tracking, and the other one is called outside-in tracking. Inside-out tracking means that you have some kind of a device mounted on your headset that observes the world, and from that alone, you're going to track the position. So these approaches are very well suitable for mobile head-mounted displays that are not tethered. You walk around outside. You don't need any external things that help you determine the position, like cameras or anything else. You have everything on your headset already. And the most common approach to this is known as visual odometry or simultaneous localization and mapping. And that's a classic component of robotic vision classes. And we have some links on the website if you're interested in this. Outside-in tracking is a little bit simpler, but you need some kind of infrastructure, like either a couple of cameras or a magnetic field generator or something else. So here's an example of inside-out tracking. I mean, that's what you really want to do if you build a commercial headset. In this case, we have an example of Google's Tango. Tango has a whole bunch of different sensors, including a depth camera, a high-resolution wide field of view camera. Then it has an IMU, of course, in it too. So it basically does visual inertial tracking. Apple just announced that they have the AR kit also online. It's basically going to be part of Apple iOS 11, right? So they're already baking this into the operating system. And what you can do with this is you just walk around with your cell phone and it will estimate the position and orientation of the device with respect to the starting point. And at the same time, it'll have to estimate the geometry of the scene, at least sparsely. So that's inside-out tracking. It's a little bit more complicated beyond this class, so we're not going to be talking about this too much. Outside-in tracking, there are many different approaches to this, including mechanical tracking. So if you have a link to your headset and you want to track it mechanically, or ultrasonic tracking, magnetic tracking, there's optical tracking. You could use GPS, Wi-Fi, or marker-based tracking. So there's a ton of different technologies for doing outside-in tracking. When I started working on VR in the early 2000s, we worked with magnetic trackers a lot, Bohemia's Fast Track and things like that. So now we have, for example, the Lighthouse from HTC, which does it, or Oculus uses a little camera and near-IR LEDs. All of these are optical tracking solutions, and we're going to be talking about this in more detail. Our particular implementation is actually based on Something that you may remember from the 90s and early 2000s is AR Toolkit. There were a couple of seminal papers on marker-based tracking. You basically have a camera on your headset, and the camera sees a square marker. It'll detect the 4 corners in the camera image, and then will estimate the position and orientation of that marker with respect to the camera. So our mathematical approach is very similar to this. Right? AR Toolkit used it to put virtual objects on top of these markers. It's actually also implemented in OpenCV, so this is used for camera calibration and tracking of these, in this case, multi-marker systems. So the more markers you use, the better it gets, but we're just going to use 4 corners, just like the original marker-based tracking. So if you look at something like Oculus Rift, positional tracking is done with a little camera that works in IR, and there's a whole bunch of near IR LEDs on the headset that the camera will track. We don't usually see this because we're not sensitive to near IR, but the camera will see them, and they're arranged in a pre-configured set in a 3D configuration on this headset. So this is what the Rift looks like if you had a near IR camera, or if you're a mantis shrimp or some other animal that can actually see near IR. And then the problem becomes, from the 2D projections of these points in the camera image, what is the 3D pose of the 3D object if we know the relative orientation and the relative layout of these LEDs or something else on the headset? And we're going to denote the local coordinates on the right, xi, yi, zi, and we know these coordinates. What we measure are the camera coordinates, x, n and yn, and from those coordinates we want to infer the 3D pose. So intuitively, as the headset gets smaller, closer to the camera, the points move farther away. As the headset moves farther away, the points are going to be closer together. And this is exactly the information that we want to use with our algorithm to track this. So there are 4 steps involved. The first step is, first we have to get the 2D coordinates, either from a camera or some other device. Second, we have to have an image formation model that allows us to model the 3D projection from the known local coordinates on the device to this 2D projected space. And we're just going to be using the graphics pipeline, as Robert explained. So it's all very consistent with one another. Third, we need to estimate the orientation and position using this model. And then we can, for example, using the linear homography method, which is simple and fast, or with something a little bit better, which is a little bit more complicated, like the Levenberg-Marquardt nonlinear optimization. And we're not going to be talking about this, but you can read it in the course notes. So let's talk about how we get the projected 2D coordinates. In a lot of optical tracking systems, you just have a camera and these LEDs or some retroreflective marker or something else, and you just do some image processing, find the coordinate centers of these things in your camera image. We're going to be using the HTC Lighthouse, and in this case it's going to be slightly different. The Lighthouse actually doesn't have LEDs on the device. It has photodiodes that record light on the headset, and instead of a camera, an external camera, it uses a projector. So the projector is called the base station, and you can see one right there. If you haven't seen it come up, you'll see it everywhere in eTech also. And they basically scan out laser sheets through the room, just like this. So I'll show you in a second. Here's a nice video that we pulled from YouTube. On the right, you can see the base station. The base station basically first projects a sync pulse. That's a broadband pulse, goes into the whole room, and then it rotates a horizontal sheet and a vertical laser sheet through the room. And each of the photodiodes that are here represented by little balls, both on the controllers and on the headset, they're going to measure their own timing. And then all the pose estimation is done on the device, actually, right? So you don't have that feedback where you need the camera image coming back to the headset. The projector operates independently from the photodiodes, and you can have as many photodiodes as you want in this room. All they need to do is measure the relative timing between the broadband pulse and the sweep. So here's the animation. I think it makes it quite intuitive. So here's a sweep, horizontal sweep. And then each of the photodiodes measures the relative timing from the sync pulse. So the sync pulse is going to be this. Sync pulse, now comes the sweep. Each photodiode has a slightly different timing, right? And you have the sync pulse in between each of the sweeps. Right? Is that reasonably clear? And so then the photodiodes know their own 2D XY position with respect to the sync pulse that you can compute from the time it took from the sync pulse all the way until the sweep hit them. And the difference in that timing is exactly the information that we want to use for the pose estimation. So the benefit of using these photodiodes and the projector is that you can do all the computation locally on the device very fast, and it's time-stamped together with the IMU, right? So you have the same microcontroller, for example, that does the time-stamping of these photodiodes and the IMU readout, so you have the same clock. If you did it on an external computer, then they may be slightly off. So it makes it a little bit easier to fuse IMU and the photodiodes and so on. Okay, so here's the base station disassembled. You can see, or one of the older versions, you can see on the side, these are near IR LEDs that send the sync pulse. All the photodiodes will see that at the same time, and then you have two rotating drums with a laser sheet that sweep these laser sheets in horizontally and vertically. So the base station runs at about 60 hertz, but it does a combined horizontal and vertical sweep at 60 hertz. So the broadband sync comes 120 times per second in between each of these sweeps, and that acts as the reference. And then the usable field of view of the projector is about 120 degrees, so it's not too bad. So we reverse engineered it to use the Arduino for this positional tracking, and this is mostly for educational purposes so that the students can actually implement the pose tracking. It's not going to work quite as well as the commercial implementation. The Arduino was designed by Keenan Molnar, one of the TAs of my class, specifically for the class, and we have the hardware design online. If you want to use it or borrow it, we'd be happy to give some out, or you can just fabricate them yourself. So Arduino again has the TNZ and the IMU. What's more important right now is these photodiodes. So again, the photodiodes will detect the relative offset between the sync pulse and the laser sweep. And we know the exact position of these photodiodes because we designed the PCB, and you can find these values here. Each photodiode is connected to 2 pins on the TNZ, so you can detect rising edge and falling edge via interrupts. That gives you a very precise timing. And the clock is very fast on the TNZ, right? It's 48 megahertz, so that's 48 million times per second. It can poll and see if there was anything coming in from the photodiodes. So this was the connection between the TNZ and the IMU again. Okay. So these are GPIO pins that we're using for external devices, but they're not important for the pose tracking. So the photodiodes report rising, falling edges. How do we know if it was a sync pulse or a sweep? We're going to have to look at the length of how long the sync pulse was on. And there's a certain amount of time that tells you, oh, this is a sync pulse or this was a sweep. So we already implemented that in the firmware, and you can directly detect whether it's a sweep or a sync. And there are more details in the course notes. So now, once we have these 2D coordinates, how do we actually get the 3D pose? Well, there are 2 different configurations. The left side shows a 3D arrangement of photodiodes, which you'll find in most commercial headsets and the controllers, and that's a little bit more robust because you have a lot of different photodiodes. Some of them can be obscured, others can be visible, but you always need a couple of them at least. Or what we have on the right-hand side is this planar arrangement of 4 photodiodes, but they're all in the same plane. So the local z-coordinate of each of these photodiodes is going to be 0 because they're all going to be on the same plane. We just define the plane to be the PCB. So now we put it all together. This is, again, the graphics pipeline. On the upper right, we have the coordinates x, y, yi, 0. That's because the z-coordinate of the photodiodes is 0, and then 1. So this is a homogeneous coordinate. We apply a rotation matrix, 3x3 rotation matrix followed by a translation matrix, and because we always use this exact rotation and then the translation, this exact order, we can actually represent it as a 3x4 matrix instead of a 4x4 matrix. And then the other matrix that has 1, 1, minus 1 on the diagonal, that's just the projection matrix. So in this case, we don't really need the near and far clipping plane, the left and right frustum. It's really a very simple projection matrix. And the fact that the z-coordinate of all these local coordinates is 0 basically cancels out the third row of the third column of this matrix, and we end up with a matrix that has 3x3 unknown elements that transforms our 2D coordinates into the camera space or into this normalized device coordinate space. We still need to do the perspective divide, and that is the division by the z-coordinate here on the bottom. So this is the exact same thing as the conventional graphics pipeline. So now our unknown 3x3 matrix has 2 columns that represent rotations and 1 column that represents a translation. So we know that any rotation should be orthogonal, right? So the norm of each of these columns of the rotation part should be 1. And the translation isn't really constrained. But that's a constraint that we can use later. So we're going to call the combined matrix of this projection matrix and the rotation translation part, we're just going to call that a homography matrix. This homography matrix has 9 unknown values, and we're going to call it H. Now the goal is going to be to estimate this homography matrix, and from that extract then the position and rotation, right? The position rotation is exactly the position we're trying to track. The rotation is the orientation that we're trying to track, but it's going to be easier to just look at the homography matrix estimation. And this is a common problem in computer vision. You can consult any computer vision book to think about homography matrix estimation. So it just turns out that a homography matrix has only 8 degrees of freedom, even though there are 9 values in there. And that comes from the fact that you can scale the homography matrix by a scalar S here on the right. If that is a constant for all values of the homography matrix, the actual image formation, if we write it out here, which is the multiplication of the first row of the homography matrix with the point coordinates divided by the third row, it just turns out that you can pull out the S value from this image formation and it just cancels out. So the image formation is independent of this scalar value. So what we're going to be doing, and this is a standard trick in 3D computer vision, is we're going to set the 9th value of the homography matrix to 1, and we're just going to ignore the scale factor for now, and then we can estimate the remaining 8 parameters first, and then estimate the scale parameter later. So I hope this is reasonably clear. Again, there are course notes online that you can read all of this up in detail. So we're going to be estimating these 3 homography matrix elements in the following. And here we're going to write this out again. We have our values x, y, so z was 0. We have the 3 by 3 homography matrix with 8 unknown elements, and we actually measured the xy projections. This is again the perspective divide. We know xin, xyn. So all we need to do right now is we shuffle around these equations a little bit by multiplying by the denominator, rearranging the equations, and for each photodiode we're going to get an x and a y measurement. So these are the blue values here, x and y for each photodiode. That's what we measured. And we have 8 unknown values from the homography matrix. So this is an under-constrained problem because we have 2 equations but 8 unknowns. So we can't really solve it. So how many equations do we need to solve this? 8. So how many photodiodes is that? 4, right? Each photodiode gives us 1 measurement in x, 1 measurement in y. So with 4 photodiodes, that's the minimum amount of photodiodes you need to turn this into a well-posed equation system. And so what we basically do is we write this nice matrix here that has a very well-defined structure, contains all these measurements that we just took. We have the measurements on the right again, and we basically solve a linear equation system that we can write as A times H equals B. We know A, we know B, and we just invert this. For example, on the Arduino, there's a nice matrix library that you can use to invert this 8 by 8 matrix. So this gives us all the 8 values of the homography matrix, and then we still need to estimate the scale. And we're going to use this knowledge that the first 2 columns of the homography matrix should actually be normalized because they represent a rotation. And so what we're going to do is we just compute the norm of these 2 columns and compute the average of them. And that gives us a scalar factor that roughly makes this a nice rotation matrix. So now that we have the scalar, we know tx, dy, tz. That's the 3D position of the Arduino with respect to the base station. And that's pretty much it. I don't have enough time to go into detail to extract the rotation from the homography matrix. Actually very simple too. We're just going to orthogonalize these 2 measurements that we have and compute the third axis so we can also get the orientation from the homography matrix. You can read up the details in the notes, but for now the summary is we take these measurements with the 4 photodiodes, we solve a very small linear system, and out comes the position of the Arduino with respect to the base station. For best results, you probably want to fuse the orientation from the IMU and the values you get from this. We skip these details right now. These measurements can be a little bit noisy, right? So you always get a little bit of a jitter, maybe in the position and also in the orientation. So a simple thing you can do is just do a little bit of temporal smoothing, because we kind of know that, I mean, wherever we move, it's going to be close to where we were in the last time step, especially if you do this 48 million times per second, right, or at whatever rate. So a little bit of temporal smoothing usually removes a lot of the noise. And here's just a screenshot that I captured from my monitor at home. Hayato is going to show you a live demo right now also. So this is a little bit complicated. Think about Maya or some kind of a 3D modeling program. On the lower left, we see a 3D perspective of the base station. So that's our coordinate origin. And then the tracked via Arduino is the little square in the corner. On the upper left, we have a 2D XY projection. On the upper right, we have an XZ projection. And on the lower right, a top-down view, I think. Right, so it works quite well in XY, as you can see. So I'm just moving the Arduino up and down. There's a little bit of latency in here, mostly from the temporal filtering. Yeah. The difficult part is really to get the Z coordinate right, because from these 4 photodiodes, it's going to be quite noisy, right? So now I'm actually enabling the orientation. I said that I can also extract the orientation from the homography matrix, and you saw that that was very noisy. So it's almost not usable at all. So you really want to use the orientation from the IMU or do some kind of a sensor fusion. Right? Here you can see that it's going to be very, very noisy. All right. So in class we also learned about non-Levenberg marquardt, and that's being used in most camera calibration toolboxes. It's nice because it's a little bit better. It's also a little bit more expensive. So you may want to skip it. It's also being used in 3D computer vision for all kinds of camera calibration. You can also dial in lens distortion, other things. We don't really need these things for this tracking approach, but it may be useful. So the general approach is to minimize the reprojection error, very similar to the homography method, but now we can actually dial in more constraints. And we're going to optimize for 6 parameters, the XYZ position, and for example, the Euler angles, or the quaternion, or some kind of another thing, and we directly estimate that from the 2D projections using a standard nonlinear optimization technique. So if you take a look at the course notes for this, you're going to find a review of gradients, the Jacobian matrix, the chain rule, iterative optimization, nonlinear optimization using Gauss-Newton, Levenberg marquardt. If you don't know what that means, it's actually pretty straightforward, so you can read the course notes if you're interested, but it's not absolutely required to implement the positional tracking. So in summary, I showed you what inertial sensors are, how to use them, how to fuse them. I showed you how to use them for orientation tracking. I also showed you our kind of reverse engineered hack of the HTC Lighthouse and how to use that for positional tracking via the homography method. The Arduino is an open source platform for hobbyists and educators. Help us make it better. It's not perfect. The firmware can be improved for both the IMU and the positional tracking. We can probably get a lot more out of this, and also the hardware. If you're interested in testing it, using it, please send us an email. So this is at an alpha stage, and right now it's very useful, low cost for all of us, and we hope it will be useful for you too. So why don't we look at a little bit of a demo here? Hopefully it'll work. And then we're going to get to the next part of the course.
Okay, so let me start with the orientation tracking. So as Gordon has explained, you are going to implement the orientation tracking system on the Teensy Arduino. So the data set and data streamed out from the Teensy is a quaternion and streamed to a computer by serial connection. And that data is passed to a browser by using a WebSocket. And as you can see, it's a live demo. If I rotate the IMU, the axis object is rotated along with it. And as I have already shown, it can be used for stereo rendering. We mount the Arduino on a head-mount display so that you can change the scene by moving your head. And let me turn to the position tracking. Would you dim the light a little bit? hope it's going to work.
So the base station is sitting right there. Right?
Yeah. It's not working. Oh, that might be the case. Okay. It was working. Okay, there you go. Okay. Let me turn to the rendering mode. Yeah, it should automatically detect. Sorry? Oh, it was open here. Sorry. Thank you. Yep. Should be okay. Yeah. So this is using the homography method that Gordon has described. So it's a bit jaggy.
Can we dim the lights maybe?
Yeah, he's already done, but I think it interferes with the infrared light that is coming from the light over there. And if I turn to the LM algorithm, it is a little bit robust to noise, so it's a bit more smoother.
Does this have any temporal filtering?
A little bit, yeah.
So this has a little bit of temporal filtering, but you can smooth that out.
Yeah.
Okay.
Yeah. So I'm switching to Nitish, who is going to talk about the audio rendering.
All right, so our next section is on spatial sound for dummies, because this dummy is going to be very important to our process later on. So as an overview, what I'm going to go over is what exactly is sound, how do we make sense of sound in the air to hear noises, voices, and other things, how do we represent sound in a two-channel format, how do we use the two-channel format to get spatial audio, and finally, how do we deal with recorded spatial audio from the real world? So first, what exactly is sound? Well, sound is a pressure wave that propagates through a medium. It has speed that is proportional to the square root of the stiffness and inversely proportional to the square root of the density. In air, the speed of sound is 340 meters per second, and in water, it's about 4 times faster. That's all great, but what exactly is sound? So let's look at how we produce sound. Basically, what we do is we vibrate air particles in a longitudinal wave. You can kind of think of this as when you move a slinky, not up and down, but forward and backwards, and you can see those pressure waves that move forward and bounce back. Speaker drums do more or less the exact same thing to air particles, and the phase offsets between when the particles are compressed and then decompressed causes a wave front to move forward until it eventually hits your ear. When it reaches your ear, it's going to bounce around your outer ear, travel through the ear canal, hit your eardrum, and then the little tiny ossicles, that is bones, that are in your ear will vibrate and transfer the sound to the snail-looking thing called the cochlea. Once in the cochlea, there's a bunch of fluid which transfers the vibrations all the way through from the base to the apex. And the important part here is that there's something called a basilar membrane, which is where all the hair receptor cells that detect vibrations lie. This basilar membrane is thinner and stiffer near the entrance and wider and more floppy near the apex. What this means is that different frequencies will vibrate the basilar membrane differentially as a function of location, and that location on the basilar membrane is where we get our frequency selectivity in our hearing. That hearing range ends up being somewhere between 20 and 20,000 kilohertz for the typical human, though of course there are individual variations. What you see in the plot off to the side is what's called the threshold and quiet. Basically, if you were in a completely silent room with no other sounds, this is effectively the quietest sound that you can hear at each given frequency. Our highest frequency sensitivity is somewhere around 4 kilohertz, and it drops off rapidly for higher frequencies and somewhat less rapidly for lower frequencies. And of course, this degrades with age, especially at higher frequencies. Next, let's look at back to the outside of our heads, to the fact that we have 2 ears. This means that we're inherently constrained to a 2-channel audio system, also called stereophonic audio. In order to get a spatial representation of sound, those 2 channels can be used to get the interaural time differences and also the amplitude differences based on distance to each ear and scattering from, walls, your ear, and everything that changes the exact sound that reaches each ear. If we want to use this to get some sort of a spatial representation of audio, the easiest thing you can do is stereo panning. So stereo panning can be used with any sound source, including a mono sound source, and it's super easy to do, and it's used all the time in stuff like music tracks. Unfortunately, since all it's doing is changing the amplitude from being fully in your right ear to fully in your left ear and vice versa, all you can really do is project a line of sound in between the 2 speakers or earphones. This is great if all you're trying to do is, say, have a voice in someone's head, but beyond that, not very useful. So what do we need to do then? Well, one way to do it is to use 2 microphones and directly record a 2-channel audio source so that you have all the time differences and slight amplitude differences that come with 2 different locations of sound recording. There are ways to do it with either left and right configurations or an XY technique that mostly records amplitude differences. On the other hand, if you want to synthesize sound, you need to have some sort of a model in place. The ideal way to do this, or rather the simplest way to do this, would be to consider the hearing system as an impulse response for a given input. So suppose we have some sound that's some distance away from the user, and there's an impulse. Well, the sound has to take some time to travel to the right and left ears, so we'll delay that impulse by whatever necessary amount. And there's also an R² drop-off in sound intensity, and so we'll scale the amplitude according to that. Unfortunately, this has a problem, which is that if you consider any sound that lies on a circle that's equivalently far from the left and right ears, it's all the same, meaning that someone would not be able to tell the difference between any sound that lies on that circle. Luckily for us, for our spatial ability to discern location, that's not how sound works. It turns out that the scattering on your outer ear, on your head, your shoulders, your body, and other objects around you is a lot more complicated, and the amplitude profile actually looks more like that than like nice peaks. Unfortunately, this is complicated enough that it becomes nearly impossible to model it in real time for a rendered audio source. And also, you wouldn't be able to remodel this for every single person's ear shape, body shape in a reasonable way. So instead what we're going to do is we're going to turn to something called the head-related impulse response. What you do here is you capture the temporal responses at every single sound direction, which we're going to parameterize by the azimuth theta and the elevation phi. You can also have a distance parameter here, and this is really useful when you have really close sound sources, but if you assume that the distance to the sound source is relatively large compared to the distance between your ears, we can more or less ignore the distance parameter, and for simplicity in this course we do. And remember that dummy from earlier? Basically, one of the ways that you can capture a head-related impulse response is to stick microphones in the ears of a mannequin and just measure sounds from every single angle that you deem necessary. Luckily for us, there's a database called the CPI-HRTF database from UC Davis, which has already done most of this work for us. They have multiple different body shapes for dummies, and they've recorded elevations from negative 45 degrees to 230 degrees and azimuths from negative 80 to 80 degrees. You can kind of see the distribution of points in the figure over there. Of course, these are discretely spaced positions, and the way we hear in the real world is continuous throughout the space. So you do need some way of interpolating between those discrete locations. Ideally, what you do is you do a triangular interpolation between the 3 nearest points, and if you toss in the distance parameter, you can do a tetrahedral interpolation. When we store this HRIR, you're going to need to store one time series data for each location. This, for a discrete set, is going to be 2 times n theta, n phi, nt samples. And we're going to denote this for the rest of the slides as HRIR left and right as a function of t parameterized by theta and phi. So what exactly do you do when you want to use this HRIR? Well, suppose you have some mono sound source S of t, and you know where you want to put it in 3D space. The first step is to calculate where exactly that location is relative to the listener's head. Once you do that, then you can look up the head-related impulse response for the left and right ear at those angles. Once you have the head-related impulse response, all you have to do, since it's an impulse response, for those of you familiar with signal processing, is to convolve with S of t, and you immediately get the sound signal for the left and right ears. Unfortunately, since convolution is a somewhat expensive process, we can't do that directly. So instead, we'll need to take a Fourier transform so it can be a quicker multiplication in Fourier domain. The Fourier transform of the HRIR is called the HRTF, or head-related transfer function, and this is actually what you'll most likely see if you look it up. People tend to use the HRTF more just because it's more computationally efficient, and luckily we don't actually lose anything in terms of space because the HRTF is complex conjugate symmetric due to the realness of the HRIR. Finally, if we want to render more than a single sound source, it's quite easy. For most volumes of sound that are reasonable to not destroy people's ears, the superposition principle tends to hold, and you can just linearly add up all the contributions, and for efficiency you can pull out like the inverse Fourier transform over there. So how does this all apply to AR and VR? Well, it turns out that most audio representation formats don't really take into account the need for the user to be able to freely turn their heads and to detect audio from all locations. For example, if you look at 5.1 or even 9.2 surround sound, they have a set of sound signals that have been multiplexed and muxed so that they're optimized for very specific locations and sets of frequencies, and once you rotate your head, those optimized locations are somewhat less optimal. So therefore, we're going to need some way of representing sound that takes into account that the user is free to move around. So there are 2 primary approaches for this. The first is that you can just store every single sound emitter's mono sound source and its 3D location. This is fine for rendered scenes where you really do know every single object's location and what sound it needs to make. And there are actually a lot of libraries such as Fmod, OpenAL that make this quite easy to do. But if you have a real environment where there's ambient noise, capturing every single sound emitter and even knowing every single location is next to impossible. So that tends to be a intractable approach. Instead, what we're going to do is we're going to turn to a format called ambisonics, which is the most widely used format today for spatial audio. The basic idea behind ambisonics is that you want to represent the sound at a single point, in this case the listener, with some amount of directional information. If we think about the HRIR from before, we did more or less the same thing, where we recorded every single direction phi and theta, but that doesn't work for real audio sources because that means you're going to have to store several minutes, maybe even more, of audio for hundreds and hundreds of channels. That quickly adds up and just does not work. So we're going to want some sort of a lower order directional basis to represent the sound so that we can have fewer channels. This is where ambisonics comes in. And they use spherical harmonics as the orthogonal basis functions. The spherical harmonics are basis functions that exist on the surface of a sphere, and therefore we can kind of represent the full sphere of surround sound if we have enough orders of spherical harmonics. You can kind of think of this, if you're not familiar with it, as a Fourier transform equivalent for spherical surfaces, but they're not quite the same, though they're qualitatively similar. This is a visualization of the spherical harmonics amplitude at each angle, and I want to remind you that these functions exist on the surface of a sphere, even though you see somewhat electron orbital shaped things here. So all the parts that go in are actually lower amplitude encoding areas. For ambisonics, we're only going to use the first 4 channels. W is the omnidirectional component, and so this kind of gives you the sound in every direction. And then X, Y, and Z are positive and negative lobes that correspond to more or less stereo components of X, Y, and Z. If you want to record real audio with this, it turns out to be quite easy, and there are actually microphones that exist that can directly record the ambisonics format. This format is directly supported by YouTube VR and many other platforms. On the other hand, say you have a rendered source, like from before, you can take the sound source S and you can convert it to an ambisonics representation quite easily. All you need are the same angle and elevation from before, and then you can compute W, X, Y, and Z quite easily using simple trigonometric operations as shown on the slide. Of course, no sound representation system is complete without a way to actually play the sound from it, and so we'll need to set up speaker locations that correspond to a demuxing of the WXYZ sounds. One such way to do this, and this is not the best way to do it, it's mostly for teaching purposes if you want to implement it yourself, is to use a 4-speaker setup that's regularly spaced in a square around your head. What you can do here is just a simple matrix operation that takes the W, X, Y, and Z components and splits them up into the speaker components. However, for real implementations, you're going to want a larger number of speakers and a faster implementation. And luckily, Google actually provides something called Omnitone, which is a JavaScript-based first-order ambisonic decoder that works directly with all of the WebGL and other stuff that we've been presenting in the course. And they render 8 virtual speakers and then use much of the HRTF and other spatial audio stuff that I mentioned in the first half in order to mux it down to 2-channel audio for your ears. There are a lot of other resources available both online and especially from Google on rendering and implementing these HRTFs. And so if you want to look into it more, it's actually quite easy to. Just remember that audio is an integral part of the VR experience. And now I'm going to hand it over to Hayato for a spatial audio demo.
Okay, so I'm going to do the demo of HRTF with 1-point light, 1-point sound source. No, just disappeared for some reason. Okay. Okay, so we decided to use a web browser as a sound processing engine again. The reason for it was to have a consistency between the previous homework and also this homework. So we are using a web audio API to convolve a signal, the audio file, with HRTF based on the orientation information we are tracking on TNZ-Dino. So I am going to rotate the TNZ, so I am hoping that you can feel it. it may not be working well because of the echo. It works the best when you have a headphone. So if you want to try it, you can come here after the talk to enjoy it. And I'm going to pass to Robert to talk about the cinematic PR.
Great, thank you. So the last part of this course, we're just going to talk about a very brief introduction to capturing some real-world content for VR. So we talk a lot about rendering, and that's great because it allows us to put ourselves in situations that we wouldn't physically be able to put ourselves in otherwise. But sometimes we still just want to be able to put ourselves in another location on planet Earth. A great example of this that I've heard explained to me many times now is essentially streaming sports games. So if you place some type of omnidirectional camera where you can capture in stereo all views around you, you could place one of these omnidirectional cameras, courtside seats of an NBA Finals game, and then stream this to thousands of users, ideally millions of users, and have them all feel like they're courtside seats at an NBA game for a fraction of the price. So we're going to talk about how to capture this and how to do this properly. So I'll give you a quick overview of omnidirectional imaging. I'll start off with panoramic imaging and how it's actually different from what we need to support for VR. And then I'll talk about stereo and omnidirectional panoramas, which is what we need for VR, and then a couple of camera rigs to actually be able to capture this sort of information. So Jaunt VR came out a couple years ago now with one of these kind of crazy-looking rigs. And they started as a tech company. Now they're working as a production company, and they've captured some pretty amazing omnidirectional videos of people like Paul McCartney, as well as other famous celebrities. And like I said, their whole idea was to try to capture the experience of being somewhere where you may not be able to be otherwise. Not many people would be able to stand on a stage with Paul McCartney while he's playing a concert, right? So I think many other people started jumping into this area. Lytro announced, this is just actually a conceptual drawing, they actually have their own video from their new omnidirectional camera at the eTech booth. So I'd encourage everyone to check that out. I heard it's really interesting because it actually supports 6 degrees of freedom, which many of the current omnidirectional displays do not support. Google has multiple camera rigs now. Nokia has rigs. Facebook has multiple rigs. Like this is their older, bulkier version. Red has a very expensive rig where they have multiple of these cameras. And those of you familiar with Red cameras know that each of these costs $60,000. So they have, 6 of them? So it's a pretty expensive rig overall. Samsung has one. I mean, there's, Ricoh has one. There are many, many different companies that are trying to get into this space. And it's a very exciting space because it allows us to, like I said, place us somewhere else on planet Earth that we're not able to maybe physically be or can afford to be, especially on the salary of a graduate student. So let's explain the differences between panoramas, stereo movies, and stereo panoramas. So one way to capture a wide-angle field of view of the world is to use a wide-angle lens. However, very wide-angle lenses are expensive, and there actually doesn't exist a lens that is wide enough to capture a full 360-degree view. And as most photographers know, you can instead capture a sequence of images, and then, by rotating the camera between the views, and then stitch them together using Photoshop or some other tool. So we can take advantage of this principle to capture views from all around us. So the first thing we're going to start off with is panoramas. And for the point of this talk, we're going to assume that the panorama is captured with a single center of projection. So that is done by rotating a camera around its center of projection, which is essentially its aperture plane. So yeah, exactly like this. So as we rotate this camera around and capture a sequence of images, we'll essentially capture a series of pictures that can be represented like this from a single center of projection, and each of those can be represented as these planes. So if we look at the individual images So each of these produce a collection of perspective views on these picture planes that are rotated to different azimuthal directions. And if we just lay them out like this, we can see that we are capturing all of the information in the scene around us. So how do we stitch them together to make a mosaic? Well, what kind of operations do we need? Translation, rotation? Well, it turns out we actually need the perspective that transform, which again, we can define from the computer graphics pipeline. So we can do this relatively easily with a series of steps, and this is much easier when we assume a single center of projection. Things become a little bit more complicated when we don't, but there's a series of papers and a lot of research in that area. So I'm not going to go into that. I'm just going to go with the simplest method. So this first step, we can find corresponding features between pairs of images, compute the perspective from the second to first image, then warp the second image and overlay it on the first one, and then finally blend the images together, and then repeat for the next image and the next image. So this works relatively well if you only have a couple of images, 2 or 3 images, let's say, and they represent a camera rotation of less than 120 degrees. It's easy because you can just reproject them onto a single plane, like you have here. However, if you have, let's say you add in a 4th image now, and this picture is taken from a wider angle for wider than 120 degrees, you start getting these kind of weird perspective, these weird views. Because after all, where do you place this single plane to project all of these images onto? So the answer, you can still end up doing this, but you can't necessarily project onto a single plane anymore. And the answer is to actually project onto a cylinder instead. By projecting onto a cylinder, we essentially project each of the images onto a cylinder, after which we can unroll the cylinder and we essentially have a rectangle or an image. So that's a good way of encoding this information while still preserving a lot of the structure. And then what we want is, if we have the cylindrical panorama now, where each of the images are projected and splatted onto a cylinder, we can actually generate a new view from this scene by taking an arbitrary point on the cylinder and projecting that image or that view onto a plane again. And then we can have an undistorted view of that same scene. And now there's actually a really great Flash demo that describes all of this, and I'm just blatantly stealing a lot of these slides from Mark Lavoie's course, CS178, that he used to teach at Stanford, but it's a very, very good explanation of this entire pipeline. And the Flash demo, if you just Google CS178, it's a really good way of understanding how all of this works. So if we go back to this image of the Matterhorn and we end up projecting onto the cylinder, we end up seeing, when we splat the images, we get these kind of rounded edges. When we blend them together, they all go away, and we have a nice view of a wide field of view of this one scene. So we can project onto cylinders. We can also project onto things like spheres. The problem with projecting onto spheres is that it's difficult to end up representing it as a rectangular image. You end up getting this very strange warping at the top that you can see there. Essentially, there's a bunch of different types of reprojections that you take from, essentially have been inspired from mapping a globe onto a 2D planar image, but they all have their corresponding distortions. So there's no easy way of representing it as a rectangular image without really having extreme stretching or these distortions. So let's move on to just stereo imaging that we've been talking about earlier. A first instinct that people may have is to just take 2 cameras that are in stereo and just capture 2 panoramas, one for each position, like so. So instead of having one center of projection, you now have 2. And at first glance, this may look cool. We're capturing stereo information. That's nice. We can end up displaying this on a VR display. But if you look a little bit more closely, this isn't exactly the case. What we end up having is, if we look in this direction, we end up having stereo information. Each camera is capturing a slightly different viewpoint of the same scene, the horizontal parallax we were talking about before. If you look to the opposite side here, we still see this same parallax information. But if you look to the side now, both cameras are essentially pointing along the same ray. They're capturing the same information, essentially. You don't have this horizontal parallax anymore. The same goes for if you look in the other direction here. So a slightly better illustration is here presented by, again, an image from Google, where if we look to an axis orthogonal to the line generated along these two centers of projection, we end up having correct disparity, but as we go closer and closer to that line connecting the two centers of projection, we end up having no disparity. So we can't really end up using this for a stereo display for a VR display, because if we have correct stereo information on one angle and then rotate our head and suddenly lose it all, that becomes pretty disorienting and wouldn't be a very convincing experience. So what we really have to do is support stereo information in all directions, regardless of our head rotation. Okay, so these two things, let's say right now, aren't good solutions for a VR system, for capturing content to be displayed for VR. So because we need to, like I said, account for this head rotation. So when we look in one direction like this, we have, again, some distance between our eyes, the IPD, or interpupillary distance. And when we rotate our head, we actually end up looking at a scene from a different center of projection now, right? We can see that the cameras are now are located at different centers of projection, and they actually view the scenes from different viewpoints. So actually, the ideal representation that we'd like to have is one where we essentially take a pair of stereo cameras, put them on some arm, and rotate them around and capture a full 2D information at every single point, representing an image at every different center of projection. And this is essentially what we would like to have in a stereo panorama, a camera where we're able to capture the viewpoint from multiple centers of projection corresponding to every single head rotation, essentially capturing a full stereo view at every single head rotation. So the problem with this type of approach is, well, I mean, there's just too much data. Essentially, if we wanted to account for every single head rotation, let's say even 1 degree, that's like the resolution of the angular resolution we'd like to support, we still have to support 360 stereo pairs for every single frame of a camera. And that just becomes very unwieldy very, very quickly. So there have been a couple of different approaches to kind of cutting down or representing this in a slightly more manageable form factor. And the one that's kind of taken over and become kind of the clear winner here, maybe not clear winner, but the currently employed approximation is the omnidirectional stereo, or ODS, approximation. So instead of essentially having this view where at one rotation of the head we have a full 2D image captured, we instead only capture the rays that are orthogonal to this viewing circle. And what you'll see is that at any given position of the head, we'll see a slightly warped view of the scene from that head orientation, right? Because these rays in this omnidirectional stereo format don't exactly match the ones that we would expect to see in that location. But it turns out that the distortions that we end up perceiving in this ODS format, they're especially, the distortions that we end up perceiving are manageable and not extremely noticeable. There are some distortions, but it's a pretty good approximation, and it cuts down on the number of rays that we have to capture and store in our stereo panoramas. And this omnidirectional stereo format was introduced by Ishiguro et al. In 1990, and then later by Peleg et al. In 2001. So what we have is, for the omnidirectional stereo approximation, essentially we have two two cylindrical panoramas that we're capturing, essentially, one for the left eye and one for the right eye. The one for the left eye is indicated by the arrows in red and essentially just captures the rays tangential to this viewing circle, and the one on the right eye does the same, but for the indicated by the blue arrows here. And effectively what this does is you can think of it as two slick cameras rotating around some center of rotation as this one, and at every point it's just capturing the center ray of this camera. And you can see that directly if we just take the center pixel of what the camera captures and just drop it into a panorama and start adding them in a buffer, that essentially is the ODS panorama. And it's popular and used by YouTube VR, Google Daydream, and Facebook, and just kind of a format that fits well into the current pipeline of streaming and processing videos, because we can easily represent it as just two panoramas, two stereo panoramas. Now, the interesting thing is for uploading one of these panoramas to YouTube, it essentially just takes one eye's view and has that be the normal video. And for every frame, it actually takes the entire other eye's view and shoves it into the metadata for that image. So your image is actually quite large, but what you end up seeing is having one eye being actually the image itself and the other eye's information being stored as the metadata. And there is a tool you can download from YouTube that will automatically, format your videos that you have, the two stereo videos that you have formatted in this ODS format. So the comparison to mono is that now we have a different center of projection for every one of these head rotations. In the mono panorama, we had a single center of rotation for all the different views that we captured. So I talked about the idea of omnidirectional stereo, but I haven't really shown you how to capture one yet. The original papers in Peleg et al. And Ishiguro, they essentially took a single camera that was mounted on an arm displaced away from a center of rotation. And then they opened up two slits on this camera, and as they rotated it around, that essentially traced out the rays tangential to this smaller viewing circle that you see in the middle there. So the slit on the left side of the camera corresponded to the rays that were perceived by the right eye, and the slit on the right side of this camera, as you can see there, the left ray, were the rays that end up going into the left stereo panorama. And this camera rotated around its center of projection and captured a series of images that were then put together, and just the rays were directly extracted and placed into this omnidirectional stereo panorama format. So clearly the limitation here is that they couldn't capture any dynamic data because it took a long time to capture these series of images. They could only really take stills. So then the community, well, obviously for VR specifically, wanted dynamic data. It's more interesting, it's more engaging. So the community essentially went on to creating rigs of these cameras to try to achieve the same effect. So this is the Google Jump camera, which is a series of GoPros placed along some circle, and each of them point outwards into the world. So the idea here now is obviously we don't have a continuous kind of collection of images as we do if we were to sweep a camera around the scene, but we have a discrete number of them, and they're overlap by the adjacent cameras overlap quite a lot. Adjacent cameras have an overlapping view of the same scene. And with that, actually, the idea is to generate or interpolate views between adjacent cameras, and then, again, pull out the appropriate rays to put into the omnidirectional stereo panorama format, as indicated by this pretty nice GIF. So you have cameras 1 and 2 with differing views from a different center of projection, and then you can interpolate the views using an optical flow algorithm between the two cameras, and then extract the rays that you would then put into this omnidirectional stereo panorama. Again, just taking the center rays or the rays that are tangential to whatever viewing circle you decide to choose. Now, these types of approaches of using camera rigs, and this is kind of what the industry kind of gravitated towards right now, there are a couple of limitations, specifically that, well, whatever limitations optical flow has. So very close by objects that have occlusions and very large disparities, they tend to have certain errors. So in figure A there, that's supposed to be a gorilla. It's kind of hard to make out that though. They also have problems with thin structures. The optical flow algorithm sometimes misses these thin structures with semi-transparent surfaces, and just anything that may cause a flow mismatch like specularities. So that's one limitation, but another one that is kind of hidden and not really talked about that much is the amount of data throughput and compute time needed to generate these omnidirectional stereo panoramas. So in the Facebook Surround 360 camera, the amount of raw data captured at every second is 17 gigabits. Now, that's quite a large number just to offlink from the camera itself. So they actually have an optical offlink. They have a whole server with fiber cables coming out of the camera to stream into a server that you don't see in any of the videos that they capture. So, that's not a very practical solution. Also, the amount of compute to create this high-quality optical flow interpolation between the cameras can be very expensive because you really need to get a lot of things right. Temporal consistency is critical between frames. We are very sensitive to temporal flickering and changing between images, so you have to be very sure to be temporally consistent across frames. So the Google Jump paper ensures this, but the compute time for these more complicated optical flow algorithms that tries to get all these small details correct can be very expensive, from days to weeks even on a conventional computer, or minutes to hours, even when running on a huge data center. So the problem here is that, well, you need a large data center maybe to be able to run or capture data and then stream it in real time. So we actually have proposed a slightly different approach to a lot of this, to these camera rigs, in that we try to trade off some of the computational complexity for mechanical complexity by taking two slick cameras, so essentially taking the idea from the initial Peleg et al. Paper and spinning it at very high frame rates, and essentially with minimal computational complexity, actually none at all, we're able to capture omnidirectional stereo formats and immediately be ready to stream them to the public. So this camera consists of two slit line sensors, meaning they only have essentially a 4096 by 2 sensor. And they're able to refresh at very, very high frame rates, so that allows us to actually not have the motion blur that would be induced if you just use a traditional camera. We have 175-degree fisheye lenses that allow us to get a very large vertical field of view, some mounting brackets that allow us to put this all together, a rotary stage, and a slip ring that allow us to actually provide the mechanical support for this, to allow us to spin at high frame rates. Oh, and one thing I should mention is that we'll be presenting this paper at SIGGRAPH Asia in Thailand, so this is just a very short introduction to this. But essentially here we can see that we can capture omnidirectional data once it starts playing. Right now we can capture at, I think this was captured at 3 FPS, but right now we can capture at 5 FPS. The limitation currently is, as any mechanical system, the mechanics. The slip ring actually degrades signal integrity as we spin up to higher and higher frame rates. So that is something to look out for, but we're thinking of changing the data offlink from a slip ring to an optical offlink potentially. We also build this in a low-cost version that we had some students in our class use, and we essentially have the same version built out of Raspberry Pis and just off-the-shelf components from Amazon. We have the list of all of these components if anyone is interested in building one of these yourselves on our site, and we'd be happy to talk about this type of system. It's a very low-cost system, and it works on the exact same principle as our high-spinning version. So today I talked about panoramas and how they're different from stereo imaging and from stereo panoramas specifically, and why we can't just take two panoramas, put them next to each other, capture those and display them on a VR display. We need to actually capture stereo information for every head rotation. So with that, that'll be the end of my session, actually the end of this course, and I think we'd like to open this up to questions if anyone has any. We're all around here, until the end of the course, which is 15 minutes from now. We'd be happy to take any questions for those of you that are interested in learning more about our course or anything that we presented here today.